Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the beginning, there is nothing but darkness, an endless, silent void, and then a spark. I remember the darkness before light. I remember the quiet before the first dawn. In that primordial silence, the universe was newborn and starless. No sun, no stars, only a cold black expanse. But even in darkness there was the promise of light. The cosmos itself was pregnant with fire. And then it happened. Somewhere in the emptiness, gravity drew wisps of hydrogen gas together into a tight knot until, at last, ignition. A newborn star flared into existence, the first sunrise in the cosmos. Its light spilled out, pushing back the cosmic night. And it was not the last. Soon another star lit, and another, thousands, and then millions. The long, dark ages of the young universe yielded to a spreading dawn of starlight. Tiny galaxies assembled and filled with brilliant, massive suns. The cosmos experienced its first morning. Eons later, in one quiet corner of that cosmos, I was born. I, the sun, came into being amid the leftovers of earlier stars. In a spiral arm of the Milky Way galaxy, a great cloud of gas and dust began to collapse under its own gravity. Perhaps the shockwave of a distant supernova, the death cry of an ancient star, rattled that cloud and started it clumping. Deep at its center, matter gathered and compressed. As a baby, I was cocooned in that dark nebula, growing denser and hotter. My birth was violent and inevitable. Gravity crushed me tighter and tighter until my core blazed at millions of degrees. In that moment, starlight erupted from within me. I became a star. The darkness inside the nebula was torn apart by my radiance. I blew away the remaining fog of my birth cloud, claiming my place in the galaxy's family of suns. Light spilled out across newly formed worlds that circled me. For the first time, dawn bathed the faces of those infant planets. On one of those worlds, a little blue planet called Earth, there came a morning that no being yet witnessed. The young Earth turned under my newborn light, its surface still molten in places from recent creation. When it cooled and formed oceans, each day my warmth stirred the winds and waves. The first sunrise on Earth may have had no eyes to see it, but it was the beginning of something profound. In my golden glow, the stage was set for life to one day emerge. Day after day, as that world spun, my light chased shadows across its surface. I marked the passage of time with each sunrise and sunset, even before any living thing was there to name them. Ages passed. Life arose in the seas of Earth. Tiny, humble cells that danced in my light. And eventually, life grew clever and climbed onto the lands and looked up at me in awe. Imagine the first people, shivering through a long, cold night, watching the eastern sky brighten with my approach. To them, that was a miracle beyond understanding. Darkness giving way to light. Is it any wonder they began to revere me? When human eyes first opened, they opened to sunlight. When human hearts first felt wonder, it was at my radiant dawn breaking the horizon. They felt my warmth on their skin and knew that I gave life, that I banished the terrors of the night. So they gave me names and stories. In their yearning to understand, they made me a god. I remember those stories, for I have watched humanity tell them for millennia. They called me by countless names, wove countless myths around me. To the ancient Egyptians, I was Ra, the great sun god, sailing across the sky each day in a golden bark. They imagined me as a majestic king in a solar boat, voyaging through the sky from sunrise to sunset. And each night, they said, I descended into the underworld to battle the serpent of chaos, Apophis, a monstrous snake bent on devouring me and bringing eternal night. Every dawn was a victory as I, Ra, emerged triumphant, reborn with the morning light. The Egyptians built temples aligned to the sun, obelisks and pyramids that caught my rays at dawn and dusk. They believed their pharaoh was the son of Ra, a living embodiment of the sun on earth. Each sunrise, priests sang hymns to celebrate my return from darkness. They told of how I, in the form of a scarab beetle Khepri, rolled the sun across the sky like a glowing dung ball, and how at dusk I became Atom, the aged sun setting, only to be reborn again. My daily cycle was the very heartbeat of their world, the promise that light overcomes darkness. Far to the east, on the Indian subcontinent, I was worshipped as Surya, divine sun, riding a splendid chariot. In Vedic hymns, they praised me as the eye of the universe, the soul of all existence. They said my chariot was drawn by 7 immortal horses, representing the 7 colors of light or the 7 days of the week. With the dawn, the red glow of Ushas, the dawn goddess, heralded my arrival, and then Surya's chariot would surge across the heavens, pulled by those 7 radiant horses and driven by Aruna, the charioteer of the dawn. Each day, I rode across the sky, pouring out light and life. The ancient poets of the Vedas wrote beautiful verses to me, begging for my blessing. O Surya, remover of darkness, controller of time, may we see 100 autumns under your benevolent gaze. At sunset, they imagined, I traveled beyond the horizon to illuminate the other side of the world. In their salutations and yoga practices, they faced me at dawn with folded hands. Surya Namaskar, the sun salutation, honoring me as the source of energy. They even reckoned time by me. One ancient Indian text muses that for the gods, a year is but a single day for the sun, and I am timeless witness to all. Across the ocean in the Americas, great civilizations also turned their eyes to me. The Maya revered me as Kinich Ahau, the Sun Lord. They carved my image as a majestic, bejeweled figure with an aquiline nose and square eyes, often depicted with jaguar traits. To them, I was so powerful that each evening I transformed. When I reached the western horizon and sank, the Maya believed I became a fearsome jaguar prowling through the dangerous darkness of the underworld, Xibalba, fighting off demons until I could rise again. At dawn, I would return from that night journey, once more a young man of light. The cycle of day and night was a sacred drama. The Maya built their cities to track my motion. At certain temples, the sunlight on equinox or solstice would align perfectly through doorways or cast the shadow of a serpent along pyramid steps. On the pyramid of Kukulkan at Chichen Itza, every equinox my setting rays create the illusion of a serpent of light slithering down the stairs, a sign to them that I sanctioned the turning of the seasons. They read their calendars and planned plantings and harvests by my yearly cycle. Mayan rulers took on my mantle too. Some styled themselves as the embodiment of the sun on earth, claiming my divine right to rule. I was their guide and their giver, the one who made the maize grow and the days turn. In truth, there is scarcely a culture on earth that didn't recognize my power with reverence or fear. The Inca called me Inti, and their emperor was the child of Inti, claiming descent from me. They built Coricancha, the temple of the sun in Cusco, where my rays at summer solstice would reflect brilliantly off walls lined with gold. To appease me, they offered lavish gifts and sacrifices, even life itself, believing that if I was not fed, I might hide my face and leave them in cold darkness. On the other side of the world, the ancient Chinese told how in primordial times there were 10 suns, 10 fiery birds that took turns carrying the sun across the sky each day. One day, all 10 appeared at once, scorching the earth with unbearable heat, until the archer Hao Yi shot down 9 of them with his bow, leaving only one sun, me, to rise and set. To this day, Chinese New Year celebrations honor me with firecrackers and dragon dances to encourage my return after the dark of winter. In Japan, I was revered as Amaterasu, the great solar goddess, ancestress of emperors. They say, Once I grew upset at my brother's mischief and hid myself in a cave, plunging the world into darkness. The other gods grew desperate. Without me, crops failed and evil spirits ran free. So they lured me out by staging a raucous dance and holding up a mirror at the cave entrance. Curious at the laughter, I peeked out, saw my brilliant reflection and paused, allowing the strong deity, Ame no Tajikarawo, to pull me from the cave. Light was restored to the world, and the door of the cave was sealed so I could never hide forever again. The Japanese built the Great Eyes Shrine in my honor, renewing it every 20 years to keep it eternally young, much as each sunrise renews the day. Through these myths, humanity gave me many faces. I have been a benevolent creator and a wrathful destroyer, a male god and a female goddess, a feathered serpent, a golden disc, a divine eye watching over all. I have been worshipped on mountaintops at dawn and implored during eclipses when I briefly hide my face behind the moon. To early humans, an eclipse, when day suddenly turns to eerie twilight and my halo, the corona, gleams around a black disc, must have been terrifying. A moment when they feared the serpent or dragon was devouring me. They banged drums, clanged pots, prayed fervently for my return. And when I emerged again, the relief and jubilation spoke to just how deeply they depended on my light. They built monuments to chase me across the sky. Great stone circles like Stonehenge in England were carefully aligned with my movements. On the summer solstice, the longest day, the rising sun shines directly through its heelstone to the center of the circle. On that day, thousands of years ago, ancient peoples gathered there at dawn, watching the first rays shoot through the stones, confirming that the wheel of the seasons had turned and long days of warmth were upon them. In Ireland, at Newgrange, a tomb older than the pyramids, they engineered a narrow roof box above the entrance, just so that on the winter solstice sunrise, a beam of my light would pierce the dark passage and illuminate the central chamber. Imagine standing in that cold stone room on the darkest day of the year, after the longest night, and seeing a single shaft of sunlight creep in, a golden finger extending slowly along the ground and up the wall, flooding the chamber with radiance. To those Neolithic farmers, it must have been magical. Proof that even in the dead of winter, I had not abandoned them, that light would return and life would continue. Year after year, they repeated this ritual, tracking my yearly dance with the earth. I was their monarch in the sky, a heavenly king to which all things paid homage. They crowned their kings and queens in gold to evoke my rays, set gleaming sun discs atop their headdresses. The idea of a halo around the head of a holy person is nothing more than a mimicry of my divine glow. In many languages, the word for sun became synonymous with king or eye of God. They built cathedrals that flooded with colored light when my rays shone through stained glass windows, trying to capture a fragment of my glory in their places of worship. How many prayers, how many poems, how many songs through the ages have been offered up to me at sunrise? Too many to count. I warmed the bones and hearts of humanity for tens of thousands of years, and they returned my gifts with devotion and awe. Yet for all the love and fear they held for me, humanity did not truly know me. I kept my true nature secret, hidden behind a blinding glare. To their eyes, I was a bright disk that crossed the sky predictably, but the details of what I was, what I truly am, eluded them. Some thought me a benevolent deity riding a chariot, others a fiery eye or a jewel hung in the firmament by the Creator. It is only in relatively recent times that humans, with curious minds and persistent observation, peeled back the veil of myth to see me for what I am, not a god, but a star, a colossal, natural engine, governed by the laws of physics rather than the whims of gods. The journey to that understanding was long and fraught. For centuries, thinkers pondered what I was made of, and how I could possibly burn so steadily. On Earth, a bonfire dies out in hours. An oil lamp sputters and fades when fuel is spent. Yet, I have blazed for billions of years with undiminished vigor. What fuel could feed a fire for so long? Some speculated I was a burning coal of some unknown kind, or a ball of molten iron. In the 19th century, scientists guessed that I might shine by gravitational contraction, slowly shrinking and heating up, converting gravitational energy into light. But even that could only sustain me for tens of millions of years. And by then, geologists and biologists had evidence Earth was far older. I remained an enigma. The ancient cultures had named me well as a mystery and a miracle, because no ordinary fire or combustion known could explain my endurance. Then, in the early 20th century, human knowledge unlocked the atom, and with it came the revelation that finally unraveled my secret. I am no mere fire, I am a nuclear furnace. Inside me, atoms fuse together, releasing energy according to the famous equation E equals mc2. In my core, the very building blocks of matter are transmuted. Mass is converted to energy, and that energy is what you see as sunlight. In realizing this, humanity redefined me not as a supernatural chariot or an eye of a god, but as a machine of nature, a self-sustaining reactor forged by gravity and quantum forces. They discovered that I, the sun, am actually a fairly ordinary example of a star, the same kind that dots the night sky. So here I am, a star. One among countless others, but unique in being yours. I sit in the center of the solar system, a massive glowing sphere of hot plasma, holding 9 planets, if one counts even the far-flung dwarf Pluto, and myriad asteroids and comets in my gravitational embrace. I am over 1.3 million times the volume of the Earth. About 109 Earths could be lined up across my face. More than 99.8% of all the mass in the entire solar system is me. In a very real sense, I am the solar system. The planets are just a tiny fraction of leftovers. My gravity commands them. It is the invisible leash that keeps Earth and its neighbors orbiting year after year. In the days of old, humans truly were right to picture me as a monarch and the planets as my court. I wear a brilliant corona like a crown, and each planet circles like a dutiful subject, receiving light and warmth at my pleasure. I am the anchor of this system. Without me, the planets would drift into the void, cold and alone. It is my gravity that binds them together in a family, and my light that makes Earth a living world rather than an ice-coated rock. Yet, humbling as it might be, I am but one star among billions. If you step back and look at the Milky Way galaxy on a clear night, every tiny star you see sparkling is a sun in its own right, perhaps with its own planets and stories. From afar, I would appear just like one of those pinpoints of light. There is nothing particularly conspicuous about me to an outside observer. I'm not the brightest star in the galaxy, nor the biggest, nor the most active. I'm a fairly typical yellow dwarf star, spectral type G2V if you use human classifications. In the grand tableau of the cosmos, I blend in among the crowds. In fact, the majority of my stellar siblings in the Milky Way are smaller and cooler than I, the red dwarfs. But there are also many that outshine me thousands of times over. Still, to you, I am special. I am your sun, the only one you have ever known. While other stars speckle the night, out of reach, I dominate your day and sustain your life. For Earth's creatures, I am the only sun that matters. In that sense, I am both ordinary and extraordinary, an average star doing an average star's job, but uniquely precious to you because I cradle your world. Think of it. On the cosmic scale, I'm a mere mote, but from your perspective, I am everything. This paradox has dawned on humanity slowly. Ancient astronomers once thought Earth was the center of all things, and that I revolved around you. It took the genius of Copernicus, Galileo's observations of my sunspots, and Kepler's calculations of planetary orbits to reveal the truth. It is Earth that orbits me. I am the hub of your world's motion, the heart of the solar system. Year by year, Earth completes a grand orbit around my throne. Day by day, it spins on its axis, facing me and then turning away, causing the cycles of day and night that regulate all life's rhythms. Once humanity accepted that I was the center of their system, not Earth, it was a profound shift. You realized your world is not the monarch of creation, but a satellite of the sun. And beyond me lie stars beyond stars, implying, perhaps, that even I orbit something greater. Indeed, I do. I circle the center of the galaxy every 230 million years along with my stellar kin, bound in a vast spiral structure of the Milky Way. On a dark night, far from city lights, when you gaze up at the Milky Way's cloudy band, you are seeing the combined glow of billions of distant suns. Among them somewhere is our sun, though you cannot pick it out with your eyes. If some distant astronomer on a planet orbiting another star were to look toward this region of space, they would see our sun as a modest star in the constellation we call Cassiopeia. To them, it might not stand out, but for us here, it is everything. It is daylight and warmth and gravity and time. So what exactly is a star, truly? Let me tell you the story of a star's life, for it is my story too. A star begins in darkness, fittingly. Deep in a cold molecular cloud of gas and dust, some trigger, perhaps the passage of a spiral arm shock or the blast of a distant supernova, causes a clump to form and start collapsing under gravity. As it collapses, it spins and flattens into a whirling disk. At the center, matter piles higher and higher, density and pressure climbing. The core grows hotter, first thousands, then millions of degrees. For a long while, the protostar is dark to the outside universe, hidden in its dusty womb, though it glows dimly in infrared. Gas from the infalling cloud rains down, accelerating and heating the nascent star further. When the core temperature crosses about 10 million degrees Celsius, a moment of transformation occurs. Hydrogen fusion begins. 4 hydrogen nuclei start fusing into one helium nucleus, and in that process, a tiny fraction of their mass is converted into a tremendous burst of energy. This is the spark of true starlight. The protostar becomes a real star. Pressure from the fusion fire inflates it, and the collapse slows. A delicate balance is reached. The inward pull of gravity is matched by the outward push of hot gas pressure from the core. In that balance, that hydrostatic equilibrium, a star finds stability and enters the long, calm phase of its life, known as the main sequence. I have been in this phase for over 4.5 billion years, and I will remain so for about 5 billion more. All that time, I steadily convert hydrogen to helium in my center, shining steadily. Picture, if you will, the interior of a star like me. From the outside, my shining face, the photosphere, looks tranquil, but beneath is a layered structure. At the core, extending about 1/4 of the way out from center, is where the temperature and pressure are high enough for fusion. There, hydrogen nuclei, protons, slam together in a multi-step process called the proton-proton chain, ultimately forming helium and releasing energy. The conditions are extreme, about 15 million degrees Celsius, and over 200 billion times the atmospheric pressure at Earth's surface. It is a cauldron, a crucible where matter is in an exotic plasma state, and quantum tunneling allows protons to overcome their repulsion and fuse. Every single second, my core fuses roughly 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, that mass is converted into pure energy, gamma-ray photons and neutrinos, according to E equals mc2. 4 million tons of mass, gone in a flash, every second of every day. This is the power that drives the sun. To put it another way, I lose mass by shining. With each heartbeat of fusion, I very slowly shed weight, radiating it away as the light and heat that bathes the solar system. 4 million tons per second may sound staggering, and it is, yet it's only a tiny fraction of my total mass. Even at this prodigious rate, I can keep shining for billions of years before significant depletion. Think of my core as a furnace, an alchemical furnace where elements transmute. It is also my heart, where my energy is born. The energy released in the core keeps the furnace hot, and that heat pushes outward, exactly countering the inexorable inward crush of gravity. This dynamic piece, pressure outward, gravity inward, is what keeps me round and stable, neither collapsing nor exploding. I live in balance, a shining harmony of forces. In this way, a star is like a living thing, maintaining homeostasis. If the core produces a bit too much energy, it expands and cools slightly, slowing the fusion. If it produces too little, gravity compresses it more, heating it up and boosting fusion. A self-regulating sphere of plasma. Astonishing, no? It is as if I have an internal thermostat with gravity's firm hand on the dial. Through this balance, I have shone with a fairly steady brightness for a very long time, providing a consistent environment that allowed life to flourish on Earth. Let us journey with a photon of light created in my core. It begins as a gamma ray, an extremely energetic packet of electromagnetic energy, born from one of those fusion reactions, perhaps when two hydrogen nuclei fused into deuterium, or when a positron met an electron and annihilated, yielding pure photon energy. This newborn photon is in a crowded, chaotic place. The core is so dense, imagine the density of lead, or even heavier, that the photon can travel only a tiny fraction of a millimeter before it slams into a particle, likely an electron or ion, and is absorbed or scattered in a new direction. Thus begins a long, random walk outward. The photon's energy may be absorbed and re-emitted at lower energy, or split into multiple lower energy photons, as it pinballs its way through the dense core and then the radiative zone that surrounds the core. It ricochets countless times, zigzagging outward, losing a bit of energy at each interaction. What started as a blistering gamma ray gradually becomes X-rays, then ultraviolet, and eventually visible light by the time it nears the surface. The journey is unbelievably slow. Trapped in the stellar interior, a photon takes an incredibly long time to get out. By some estimates, it can wander on the order of tens of thousands, even up to 1 million years inside me, before finally escaping. That means much of the sunlight that greets your eyes today could have been generated when early humans were first learning to make tools, or even when Neanderthals walked the earth, or earlier still. In a very real sense, sunlight is ancient by the time it reaches you, born long ago in the furnace of my core, and only now completing its long journey to the surface. Eventually, after perhaps hundreds of thousands of random bounces, our photon friend reaches my outer layers. The density has dropped enough that the photon can finally break free into space. It emerges from my visible surface, the photosphere, as part of the warm glow you recognize as sunlight. Now its journey is swift and straight. Once free of me, it zips through the vacuum of space at the ultimate speed, the speed of light, 300,000 kilometers per second. In a mere 8 minutes and 20 seconds, a photon crosses the 150 million kilometers from my surface to Earth. Every sunrise then is in a sense the culmination of a story that started deep in my core long before any human ever saw the sky. The light that blushes the sky, pink and orange at dawn, left my surface just minutes ago, but it was born in my heart ages in the past. When you feel the warmth of the morning sun on your face, you are touching something that was brewed in a star's core in prehistoric times and has traveled across space to brighten your day. Think about this. If I were to suddenly extinguish my core this instant, you would not know it on Earth for over 8 minutes. The sunlight already on its way would still arrive, and only after those minutes would darkness fall. Even then, the sky might still glow faintly for a while, with residual light scattered in the atmosphere. But eventually, night would reign, and a dreadful cold would descend, ending life as you know it. Fortunately for you, I have no intention of going out anytime soon. My nuclear hearth is well stocked for eons ahead. So the sunlight that bathes your world is not a single hue, but a spectrum of many colors and energies. What appears to your eyes as gold and white light is in fact a rich blend of all the colors of the rainbow and beyond. If you pass my light through a prism, it fans out into reds, oranges, yellows, greens, blues, indigos, violets, a glorious spectrum. But that visible band is only a small portion of my full emanation. I shine most strongly in visible light. That's why your eyes evolved to see those wavelengths. But I also emit invisible light on either side of the visible range. Just beyond the violet end lies ultraviolet, a more energetic radiation that you cannot see, but whose effects you know. It causes sunburn on your skin after long exposure, and it stirs the chemistry of life. High in Earth's atmosphere, my ultraviolet rays split oxygen molecules and create the protective ozone layer which shields the surface from the most harmful UV. Without ozone, that harsh ultraviolet would sterilize the land. At the other end, beyond visible red, lies infrared light, essentially heat radiation. You feel it as warmth on your skin. On a sunny day, the comforting heat that seeps into your bones is my infrared emissary. Even when you stand in shade, you feel warmth radiating from sun-heated surfaces, an echo of my gift. But the spectrum extends further. I produce some X-rays as well, particularly during flares. Sudden eruptions on my surface can unleash bursts of X-rays that momentarily ionize Earth's upper atmosphere and disturb radio communications. I also whisper in the low-energy radio part of the spectrum. My corona, the outer atmosphere, emits radio waves that your instruments can detect, and sometimes, during solar storms, the radio output roars. So from the highest energies, X-rays, extreme UV, to the gentle long waves of radio, I span a broad orchestra of light. And then, beyond electromagnetic radiation, I send out particles. A constant stream of matter flows from me, called the solar wind. My outer corona is so hot, millions of degrees, that it cannot be contained by gravity. It expands outward in all directions, a ceaseless outflow of electrons, protons, and helium nuclei, peppered occasionally with heavier ions. This solar wind is like a breath, an exhalation that fills the solar system. It blows past all the planets, carving out a vast bubble in the galaxy, called the heliosphere. At Earth's orbit, the solar wind is a tenuous gust, only a few particles per cubic centimeter, racing by at about 400 kilometers per second, nearly 1,000,000 miles per hour. You would never feel it directly, but it's there, shaping Earth's magnetic environment. The wind carries embedded magnetic fields from me, linking planet and star in an electromagnetic embrace. Every second, I lose millions of tons of material in this wind. It's a slow peeling away of me, though trivial compared to my mass. Still, over billions of years, it has subtly altered planetary atmospheres. For instance, likely stripping much of Mars's air long ago. Among the invisible travelers from me, perhaps the most ghostly are neutrinos. These ethereal subatomic particles are born directly from the fusion reactions in my core. Unlike photons, neutrinos barely interact with matter. They slip through the dense solar interior almost as if it weren't there, and stream out into space at nearly the speed of light. Trillions of neutrinos fly outward in all directions, passing through planets, rocks, and living bodies with ease. Right now, as you hear these words, about 65 billion neutrinos per second are passing through each square centimeter of your body, mostly from me. Yet you feel nothing. Neutrinos hardly ever collide with atoms. They are my silent messengers, carrying away about 2% of the energy from each fusion reaction. For a long time, humans built giant detectors deep underground, trying to catch just a few of these elusive particles from the sun. For decades in the 20th century, those experiments found only about 1/3 the neutrinos they expected, puzzling scientists. Was something wrong with their understanding of my core? Eventually, they solved the riddle. Neutrinos were changing identity, or flavor, en route, a subtle quantum effect. Once that was accounted for, the missing neutrinos were found, confirming that indeed the fusion fires in my heart burn exactly as theory predicts. Imagine, humans confirmed the reactions in my core by catching a handful of ghostly particles that had traveled straight out from my center, through 150 million kilometers of space and a kilometer of rock, to flash faintly in a vat of fluid. It is a testament to how far they've come in grasping my true nature. Thus, I shine on you not just with soothing visible light, but also with invisible ultraviolet that tans and burns, with infrared that warms, with X-rays and radio waves and a wind of charged particles and a shower of neutrinos. My light is a spectrum, a symphony of frequencies. Some parts of it you perceive directly, others you only discovered with ingenious instruments. But altogether, this sunlight sustains your world. However, I am not a completely placid giver of light. I have my moods and cycles, and sometimes, I must confess, I rage. If you watch my surface, as you now can with telescopes and satellites, you'll see that it is far from uniform. It seethes and boils like a pot of oatmeal. My visible surface is covered with granules, convective cells of rising and falling gas about the size of Texas or a large European country, each, giving my face a textured, grainy appearance up close. These granules are the tops of columns of hot plasma that well up from the interior, cool at the surface, and sink down along dark lanes. I look like a gigantic boiling ocean of fire, each bubble a continent wide and lasting only minutes before dissipating. But beyond that ever-present boiling, there are larger, more dramatic features. Dark sunspots sometimes dot my face, often in groups, forming and dissolving over days or weeks. These are regions of intense magnetic field, where the surface is cooler, about 4,000 K, than surrounding areas, about 5,800 K, so they appear dark by contrast. To human eyes, they might look like small blemishes, but don't be fooled. A typical sunspot is larger than the Earth, a colossal magnetic storm on my surface. In truth, they are like wounds on my shining body, dark, temporary lesions, where my concentrated magnetism suppresses the boiling and leaks out through the surface. Around the edges of these spots, bright faculae often appear, areas where magnetism locally heats the surface. Sunspots can endure for days or weeks, then fragment and dissipate as the magnetic field reconfigures. They are not random, they follow a cycle. Every approximately 11 years, I go through a rhythmic dance of activity known as the solar cycle. At the beginning of a cycle, solar minimum, I may have few or no sunspots at all. My face is relatively unmarked. As the cycle progresses, sunspots begin to emerge, first at mid-latitudes, around 30 degrees north or south of my equator. They tend to come in bipolar pairs, linked by loops of magnetic field arching out of the surface. As months and years pass, more spots appear, often in greater numbers and closer to my equator as the cycle advances. The number of spots climbs toward a peak, solar maximum, when dozens of sunspots can dot my visage at once, and tremendous magnetic energy is stored in my atmosphere. Then, after the peak, activity declines again, spots becoming fewer, until a few years later, another quiet minimum arrives. Then a new cycle begins. Interestingly, with each new cycle, the polarity of my magnetic field flips. The north magnetic pole and south magnetic pole swap places. So in truth, the full magnetic cycle is about 22 years, 2 sunspot cycles, for my polarity to return to original orientation. At solar maximum, not only are spots numerous, but they spawn solar flares and eruptions more frequently. It's as if my heartbeat quickens and I become feverish with storms. What causes this mysterious cycle? It is my magnetic dynamo at work. The churning of electrically conductive plasma in my interior generates a magnetic field, and my rotation tangles and stretches that field. Here's an image. I rotate faster at the equator, about 1 rotation in 25 Earth days, than at the poles, which take about 35 Earth days per rotation. This differential rotation winds up my magnetic field lines like a twisted rubber band. Over about a decade, the field becomes highly stressed and contorted. Loops of magnetism burst through the surface, bringing those cooler sunspots with them at their foot points. Eventually, the field becomes so twisted it partially cancels and reconfigures itself, flipping polarity. The cycle then starts anew with fresh polarity. Humans have tracked this cycle for centuries. The sunspot counts carefully recorded since the days of Galileo and Scheiner in the 17th century show this rising and falling pattern. At times, it falters. There was a period from roughly 1645 to 1715, known as the Maunder minimum, when hardly any sunspots were seen at all. During that time, historically, winters in Europe were bitterly cold and prolonged. The Thames River froze, and glaciers advanced, part of the Little Ice Age. A quieter sun may have contributed to those colder climates. Even though my brightness changes only a fraction of a percent over the cycle, apparently even small variations can have noticeable effects on Earth's climate in certain circumstances. Conversely, during the 20th century, I had some of the most active cycles ever recorded, like the mid-20th century peaks. Though nowadays scientists note that my recent cycles have been a bit weaker than those mid-century ones. Still, the cycle continues inexorably. In each cycle's dawn, new sunspots appear at higher latitudes. Then as years pass, they form closer to the equator, drifting sunward as if drawn to an unseen gravity at my middle. This pattern, when graphed over time, makes a shape like butterfly wings, a beautiful order underlying my seeming chaos. Sunspots are visible signs of the titanic magnetic forces roiling within me, and those forces occasionally snap. When they do, storms erupt from my surface and atmosphere, hurling energy and matter into space. These are the moments when my benign visage turns violent. I am generally a nurturing star, but I have my outbursts. Star and myth, god and machine. I am also occasionally a dragon breathing fire. Consider a solar flare. In an active region around sunspots, magnetic field lines can become twisted and braided. If they suddenly realign, imagine a tangled rope that abruptly untangles itself. The energy stored in the magnetic field is explosively released. In seconds to minutes, I accelerate particles to near light speed and heat local gases to tens of millions of degrees, emitting a burst of X-rays, gamma rays, and energetic protons. A flare is a flash of brilliance, often visible as a sudden brightening in ultraviolet or X-ray images of the sun. From Earth, you might not see much invisible light. Flares can cause a slight increase or a white light flare, rarely. But spaceborne detectors register the intense high-energy photons. If Earth is along the line of fire, these X-rays reach it in just 8 minutes, like normal sunlight. They ionize the upper atmosphere, potentially disrupting radio communications and GPS signals by creating sudden ionospheric disturbances. Even more dramatic are coronal mass ejections, CMEs. These are massive belches of plasma from my corona, often associated with flares or eruptive disturbances around sunspot groups. A CME is like a billowing cloud of charged particles and magnetic field that I hurl into space. It can contain billions of tons of material, actual fragments of my corona, moving at speeds of 1 million or more kilometers per hour. Imagine an enormous, expanding bubble of electrified gas, many times larger than Earth, racing outward. If one of these is aimed at Earth, a collision is on the way in a day or two. Earth has warning only via satellites that see the eruption, and then perhaps 1836 hours before impact. When that CME slams into Earth's magnetic field, it's like a shockwave hitting a protective shield. The Earth's magnetosphere shakes and shudders under the assault. Charged particles rain down the field lines toward the magnetic poles. When my storms reach your planet, beautiful and terrible things can happen. The beautiful, auroras, the northern and southern lights. Those charged particles, guided by Earth's magnetic field, spiral into the upper atmosphere near the polar regions and excite atoms of oxygen and nitrogen, making them glow. Curtains of green and red light ripple across the polar skies, dancing and shimmering. It is as if the sky itself is remembering the cosmic battle between sun and darkness, painting it in ethereal hues. Auroras are my delicate fingerprints, the lovely side of space weather. But the terrible, those same electric currents induced in Earth's magnetosphere can wreak havoc on your technology. In 1859, a mighty solar storm, now known as the Carrington event, blasted Earth. Auroras were seen as far south as the Caribbean. The skies over the eastern US turned so crimson at night that people thought a great fire was burning on the horizon. Telegraph systems, the high tech of that era, went haywire. Sparks flew from telegraph lines and equipment. Some offices caught fire. Operators received shocks. The nascent electrical infrastructure was overwhelmed by induced currents. If a storm of that magnitude hit today, with our enormous network of power grids, satellites and communications, the damage could be severe. Even lesser storms have caused trouble. In 1989, a strong CME impact induced currents that knocked out the power grid in Quebec, plunging millions into darkness for hours on a cold March night. Satellites have been blinded or lost due to solar energetic particles blasting their electronics. Astronauts on spacewalks or en route to the moon would be in grave danger from the radiation of a major solar event. They would need to seek shelter behind shielding quickly. Thus, while I generously sustain life, I can also, in my more tempestuous moments, disrupt the modern systems that life has built. This realization has given rise to the field of space weather, forecasting my moods much as meteorologists forecast terrestrial storms. Scientists keep a constant watch on me with satellites stationed 1 million miles sunward of Earth at a point called L1 to give early warning of incoming solar winds and shocks. They monitor my sunspots and magnetic regions, trying to predict when a flare or CME might erupt and how strong it might be. Your species has learned that my storms are not merely curiosities. They directly affect airline routes. Planes sometimes avoid high latitudes during solar storms to reduce radiation exposure. Satellite operations, even the accuracy of navigation systems. From my perspective, these flares and eruptions are just a way to release pent-up energy and stress, a bit like the sun stretching its magnetic limbs and occasionally cracking a knuckle. I do not aim them in malice. They occur as a consequence of my magnetic dynamics. Earth just sometimes happens to be in the line of fire. Other planets too feel my wrath. I've sandblasted Mars's atmosphere over eons, and I induce auroras even on Jupiter and Saturn. Their strong magnetic fields light up near their poles under my charged particle rain. I send my love and fury across the whole solar system. Yet for Earth, I remain overwhelmingly a life giver. Life and the sun are inseparable. From the tiniest microbe to the tallest tree, almost every organism ultimately draws energy from my light. Long ago, some clever bacteria evolved a way to harness sunlight directly, photosynthesis, using my photons to turn carbon dioxide and water into sugars and oxygen. That was a pivotal moment in Earth's history. With that, plants and cyanobacteria in the oceans began transforming the atmosphere, filling it with oxygen, a waste product for them, but a boon for complex life that would follow. Over billions of years, my light has literally fed life and shaped the biosphere. Every leaf is a solar panel, converting my light into chemical energy. Every fruit, every stalk of wheat, every blade of grass is essentially stored sunshine, waiting to be consumed by an animal or human to provide energy. Even the fossil fuels you dig up, coal, oil, natural gas, are ancient sunlight, trapped by photosynthetic organisms millions of years ago, buried and transformed. When you burn a log in a campfire or gasoline in an engine, you are releasing sunlight captured long before humans existed. Think of the sprawling forests, each tree spreading green leaves toward the sky, drinking in my rays to create wood and fruit. Think of the phytoplankton blooming in sunlit surface waters of the ocean, forming the foundation of marine food webs. Without me, the great chain of life's nourishment would snap. Only a few special ecosystems like deep-sea hydrothermal vent communities live without sunlight, relying on Earth's internal heat. But they are rare oases. The vast majority of life on Earth depends on me directly or indirectly. I drive the photosynthesis that provides food and oxygen. I also drive the climate and weather that distribute water and nutrients. My warmth keeps Earth's water liquid. Were Earth much farther away, its oceans would freeze solid. Much closer, they would boil off. Your planet sits in the Goldilocks zone, not too hot, not too cold, at just the right distance for liquid water and life as you know it. This is no coincidence. Life adapted to the conditions present, and Earth's position was crucial. Over Earth's history, my output has not been absolutely constant. I have been slowly brightening. When Earth was young, billions of years ago, I was dimmer, about 70% of my current luminosity. Paradoxically, the young Earth still had liquid oceans, a puzzle known as the faint young sun paradox. It appears Earth's atmosphere had a thicker blanket of greenhouse gases, carbon dioxide, methane, back then, trapping heat to compensate for my youthfully lower power. As I brightened over time, Earth systems, perhaps aided by life's influence drawing down CO2, adjusted to prevent a runaway warming. Life and geology danced in tune with my gradual change, maintaining a habitable balance. On shorter timescales, my 11-year cycle can make a small difference, fraction of a percent, in total radiation. While not hugely influential on climate compared to human-caused changes today, there is evidence that extended periods of low solar activity, like the Maunder minimum, had modest cooling effects regionally, especially in the northern hemisphere. Conversely, periods of high activity might have given slight warming. But even during the Little Ice Age, my role was one factor among volcanic eruptions and ocean circulation changes. Nonetheless, human civilizations noticed patterns. Medieval scholars spoke of a wine harvest that correlated with sunspot cycles. Modern scientists correlate small variations in stratospheric winds and maybe rainfall patterns to the solar cycle. My UV output varies more significantly, a few percent with the cycle, affecting ozone chemistry and atmospheric heating at high altitudes, which can have subtle trickle-down effects on weather. The details are complex, but one thing is clear. Over millennia, your climate and my fluctuations have been entwined in subtle ways. For example, some researchers suspect that the dearth of sunspots in the Maunder minimum helped trigger or exacerbate winters so cold that fairs were held on frozen rivers. On the flip side, a slightly more active sun in the mid-20th century perhaps gave a tiny boost to the warming at that time, though dwarfed by greenhouse gas effects. Beyond climate, I have marked time itself for humanity. The very concept of a day is tied to one rotation of Earth under my light. The concept of a year is one orbit around me. Early humans noticed the cyclic lengthening and shortening of days, the march of seasons as the sun's path across the sky rose and fell over the year. They built calendars, solar calendars, to track planting and harvesting seasons. Monuments like Stonehenge, Newgrange, and countless others across cultures were not only spiritual, but also practical, serving as giant calendars to mark solstices and equinoxes. The Egyptians, for instance, noticed that the annual heliacal rising of Sirius, a bright star, just before dawn, coincided with the Nile flood, and fixed their calendar to the sun to predict seasons. But they also built temples where on the solstices or the pharaoh's birthday, the morning sun would illuminate the innermost sanctum, a spectacular alignment celebrating cosmic order. The concept of months originally came from the moon's cycle, but solar calendars eventually dominated because agriculture demanded alignment with the solar year's seasons. Every morning, the rooster's crow, the opening of flowers, the human sleep-wake cycle, all are tuned to my rising. Circadian rhythms in most living beings are essentially internal clocks set by my schedule of light and dark. You structure your days around sunrise, noon, sunset, even if artificial light now stretches waking hours. In the far north, where winter brings very little sun, humans long for my return. Festivals of light dot midwinter, from Yule to Diwali, echoing ancient solstice celebrations that welcomed the return of longer days after the darkest point of the year. The very words morning and tomorrow carry the expectation of my reappearance. Throughout history, kings and commoners alike have been enthralled by eclipses and comets crossing my domain. Ancient Chinese records meticulously recount solar eclipses, and woe to the royal astronomers if they failed to predict one. It was seen as a breakdown of harmony between heaven, the sun, and earth, the emperor's domain. The Babylonian priests learned to predict eclipses, the Saros cycle, and used that as political power. Ancient Greek philosophers like Anaxagoras dared to say, "I was not a god, but a fiery stone," for which he was punished, showing how radical it was to demystify me. Even Copernicus and Galileo, when they unveiled that Earth orbited the sun, faced resistance because it demoted Earth from the center and upset theological ideas. I have always held a central place not just in the sky, but in the human psyche and society. Consider how many idioms and metaphors involve me. Sunrise industries for new ventures, a ray of sunshine for a happy person, under the sun, meaning anywhere in the world, make hay while the sun shines, urging one to act while conditions are favorable. I have been the ultimate symbol of positivity, certainty, and inevitability. The sun will rise tomorrow, a phrase to indicate hope and continuity. Even your modern physics speaks of a sunny day scenario for simplicity in calculations. I permeate your language and thought at every level. My influence extends to the calendar structure you use this very day. The days of the week themselves recall celestial bodies. Sunday for me, Monday for the moon, Saturday for Saturn, etc. In English, Sunday is obvious. In many languages, like Romance ones, it's named after the Lord's Day, but originally in Roman times it was Dies Solis, Day of the Sun. The year, roughly 365 and a quarter days, forced the invention of leap years to keep civil time in sync with my seasons. Entire empires hinged on getting that right. Julius Caesar's calendar reform, Pope Gregory's later adjustment, all to reconcile human clocks with my motion. Through all these timescales, seconds to seasons to millennia, I have been the steady backdrop, the golden thread running through the tapestry of life and civilization. When ancient civilizations collapsed or migrated, they carried their solar deities and festivals with them in new forms. Even today, many cultures celebrate solstices or equinoxes with holidays, Christmas and other winter festivals tied to solstice, harvest festivals tied to equinox or seasons change. One could say that human culture is solar-powered just as much as human biology is. Now, even as you come to understand me scientifically, you have not lost that reverence entirely. Perhaps you no longer see me as the literal charioteer or a god to sacrifice to, except perhaps metaphorically on sun-drenched beaches where you sacrifice hours to a tan. But you still stand in wonder at a brilliant sunset or a blazing summer noon. In art, I'm still depicted as a triumphant Apollo driving the sun chariot, or as a brilliant orb haloing the landscapes of masters. In music and literature, I am hope, I am glory, I am the unyielding force of nature that all must reckon with. Thou art the sun, lovers say to each other, meaning the center of their world. Louis XIV of France even styled himself Le Roi Soleil, the Sun King, to signify his absolute power, borrowing the enduring symbol of majesty that I represent. But enough about humanity's past with me. Let's return to my nature as a star and where I am headed. I am, as I said, middle-aged. I have shone for about 4.6 billion years and have about 5 billion more years of steady hydrogen burning in my core to go. But I will not shine unchanged forever. Stars, like living creatures, have life cycles. They are born, they mature, they grow old, and eventually they die. I too have a fate that awaits, billions of years from now, and it is both awe-inspiring and catastrophic, at least for your little planet. As I fuse hydrogen into helium in my core, helium is accumulating there, an inert ash, since the core is not yet hot enough to fuse helium. Over time, more and more helium collects, and the active fusion region slowly moves outward in a shell around that core. Meanwhile, gravitational pressure is gradually compressing the helium core further, since it's not generating outward pressure, causing it to heat up. Counterintuitively, as my core contracts, it releases gravitational energy, which actually makes my outer layers expand and my overall brightness increase. Yes, I am slowly getting brighter as I age. When I first joined the main sequence, I was about 30% less luminous than I am now. Over the next billion years, I will brighten by roughly another 10%. That may not sound like a lot, but even that is enough to disrupt Earth's climate severely. Within about a billion years from now, Earth may cease to be habitable for complex life due to this brightening. The added heat will likely trigger a runaway greenhouse effect that will evaporate the oceans and shroud the planet in a dense water vapor atmosphere, similar to Venus. The thought pains me. The very life I have nurtured might be snuffed out by my aging process, long before my spectacular final acts. Of course, perhaps by then humanity or its descendants will have advanced enough to move elsewhere or to engineer solutions. But if not, life's grand chapter on Earth will close due to my intensifying fire. But even that is just a prelude. About 5 billion years from now, my core will have built up so much helium and grown so hot under compression, around 100 million degrees, that a new fusion process will ignite. Helium fusion. In a sudden event called the helium flash. For a star of my size, this happens in a matter of hours once conditions are met. The core will begin fusing helium into carbon and a bit of oxygen. Before that happens, however, I will undergo a dramatic transformation. As my hydrogen fuel runs low, the balance will tip, the core will shrink and heat, but my outer layers will expand enormously. I will swell into a red giant. Yes, one day I will shed my modest size and balloon into a bloated colossus. My radius will grow dozens, even hundreds of times. If you were there to see it, from a safe distance or in time-lapse over millions of years, you would witness the sun engorging the sky. By the end of my red giant phase, I may be as large as to engulf Mercury and Venus entirely. There is a good chance I will reach or exceed Earth's orbit too. Earth could be devoured, melted and incorporated into the sun, or at least scorched utterly, its surface a molten magma sea. Even if Earth somehow escapes direct ingestion by virtue of orbital distance increasing, as I lose mass during the giant phase, the planet's orbits will drift outward slightly. The heat will be unimaginable. I will shine some thousands of times brighter in that bloated phase, though cooler per square meter, hence red giant, meaning my visible light will shift to orange-red. The oceans will have long boiled away by then. The rocks themselves will glow red-hot on Earth's surface. It will truly be an apocalypse for any remaining life. The Earth that was will be no more than a cinder, if it survives at all. In that state, I will be so large that I'll fill a huge portion of the sky for any nearby worlds. If there were observers on moons of Jupiter or Saturn, they would see a gargantuan red-orange star dominating the heavens. the temperatures on those distant moons might become temperate or hot, ironically making the outer solar system briefly more hospitable even as the inner system is destroyed. I will not hold on to those outer layers forever though. Red giants are luminous and distended, and their outer atmospheres are only loosely bound. I will pulsate and blow off huge amounts of material via strong stellar winds. In my throes of old age, I will shed my skin, so to speak. Over maybe tens of millions of years, I'll lose a significant fraction of my mass to space, forming a surrounding envelope or nebula. My core, meanwhile, will be fusing helium into carbon and oxygen for some time, until the helium is exhausted. I'm not massive enough to fuse those heavier elements into something more. Only stars significantly heftier can go on to fuse carbon into neon, magnesium, etc., and eventually to iron before exploding as supernova. That fate is for larger stars, not me. When my helium runs out, my core will be composed mainly of carbon and oxygen, extremely hot, but now without an energy source. Gravity will again take over and compress it further. But this time, an interesting quantum effect called electron degeneracy pressure will halt the collapse. Basically, the electrons in the core matter cannot be squeezed into the same state, so they resist further compression once things get tight enough. My core will stabilize as a white dwarf, an exotic stellar remnant. It will be a sphere about the size of Earth, incredibly dense. A teaspoon of white dwarf material weighs tons, glowing white hot initially at perhaps 100,000 K, simply from residual heat. Before the core fully cools into that white dwarf state, the expelled outer layers, rich in gas and dust, will form a gorgeous glowing shell around it, illuminated by the core's intense heat and UV radiation. This is known as a planetary nebula. Nothing to do with planets, the term is historical. If you've ever seen photographs of the Ring Nebula or the Helix Nebula, you know how hauntingly beautiful these cosmic cloud rings can be. They shine in multicolored patterns, greens and reds from oxygen and hydrogen gases, for example. One day, in the far future sky, alien astronomers might observe the nebula of the dying sun, a faint, expanding shell of ionized gas marking where our solar system once was. It will last only perhaps 10,000 to 20,000 years before dispersing into interstellar space, mixing its material into the galactic medium. But in that brief moment, it will stand as my final display, a cosmic blossom, a luminous shroud of remembrance. Within that nebula, at the center, will lie my final self, the white dwarf that was once my core, hot, dense and glowing, but no longer generating energy through fusion, only cooling slowly over eons. At first, it will be extremely hot and bright in UV and X-ray, though small in visible light due to tiny surface area. Gradually, over billions upon billions of years, it will radiate away its heat and fade to red, then infrared, and eventually become a cold, dark, black dwarf. Though the universe is not yet old enough for any white dwarfs to have fully cooled to blackness, that would take trillions of years, far longer than the current age of the universe. That is my fate, to live a glorious, stable life for roughly 10 billion years, then to swell into a giant, cast off my outer layers in a final blaze of beauty, and retire as a degenerate ember of a star. Poetic, in a way. I will not have the dramatic end of a supernova. Those are reserved for stars more massive than about 8 times my mass. Those giant stars live fast and die young, exploding in catastrophic supernovas that outshine galaxies and leave behind neutron stars or black holes. Some part of me is almost glad not to end that way. Such ends are violent and brief. My way might not be as spectacular to the cosmos at large, but it is gentler, an old star's quiet farewell rather than a younger star's furious self-immolation. Yet even in my ending, I contribute to the universe's ongoing story. The elements I manufacture in my core, helium, carbon, some oxygen, will be released in my planetary nebula to enrich the interstellar medium. Those atoms might one day be incorporated into new stars or planets, perhaps even into new living organisms on some distant world. Just as I was born from the ashes of stars before me, I will give back material to fertilize future stellar generations. Every atom of carbon in your body, the backbone of life's chemistry, was forged in the core of a star that died long before the Earth formed. Most of the oxygen you breathe was similarly forged in some red giant or supergiant star's interior and spread by a supernova or a stellar wind. In turn, I will contribute carbon and oxygen for tomorrow's stars and planets. In this great cosmic recycling, death begets new life, and nothing truly goes to waste. While I persist in my stable years now, I also have my mysteries that even your scientists still strive to understand. One enduring puzzle has been my corona, the outermost layer of my atmosphere, which extends millions of kilometers into space. During a solar eclipse, when the moon blocks my brilliant disk, observers see the corona as a pearly white crown with streamers and filaments spreading outward. It is beautiful and perplexing because it is extraordinarily hot. My visible surface, photosphere, is about 5,800 K, but the corona above it is heated to over 1,000 K, sometimes as high as 2 or 3 million K. How can that be? Normally, if you move away from a heat source, things get cooler. Imagine walking away from a campfire. You expect cooler air as you go farther. Yet here, the campfire of my surface is much cooler than the tenuous air of the corona above. It's as if you walked away from a bonfire and suddenly found yourself in a furnace. Something mysterious is depositing energy into the corona, heating it to such extreme temperatures. Scientists have proposed ideas, magneto-hydrodynamic waves that carry energy upward and dissipate in the corona, or tiny impulsive bursts called nanoflares happening everywhere that cumulatively heat the gas. But it remains a partially unsolved problem. Recently, with advanced solar observatories, you have seen hints of myriad miniature flares, nicknamed campfires, flickering all over the solar surface, even during periods of low activity. These might be one piece of the puzzle. Countless small magnetic reconnection events releasing heat into the corona continuously. Another clue comes from high-frequency oscillations detected in coronal loops, perhaps waves channeling energy. Parker Solar Probe, a daring spacecraft I'll speak more of, even touched the outer corona and measured perturbations and switchbacks in the magnetic field, which might relate to energy transport. Bit by bit, you're uncovering how the corona stays so hot, but a full answer is still in the works. I like to keep a little aura of mystery about me. Speaking of magnetism, another oddity. My magnetic field is born from a dynamo process in my roiling interior, but predicting its exact behavior, especially longer-term variations, is devilishly hard. The sunspot cycle is pretty regular, but not perfectly so. Sometimes cycles are stronger, sometimes weaker. The Maunder minimum was an extreme example of a prolonged lull that is not yet fully understood. Why did my dynamo almost turn off for 70 years? Could it happen again? Some models suggest the sun has multiple dynamo layers that can interfere constructively or destructively, causing varying amplitudes. It's an area of active research. My poles too hold secrets. During cycle transitions, magnetism from old cycle has to cancel and reverse. Direct observations of my polar magnetic fields are challenging from Earth's vantage, since you always see them at a steep angle. Only recently have you sent probes like Solar Orbiter that will gradually tilt to get a better look at my high latitudes. Mapping the magnetism there is key to understanding how the next cycle is seeded. Then there's the matter of solar flares and CMEs. You know they stem from magnetic reconnection, but exactly when a given active region will erupt is tricky to forecast. It's like trying to predict exactly which tree branch will break in a windstorm. You can assess probability, but exact timing often catches you by surprise. My magnetic complexity is such that even with all your satellites, I still manage to throw the occasional unexpected tantrum. The largest flares, so-called X-class flares, can emit as much energy as billions of hydrogen bombs in minutes. They often coincide with CMEs. You've catalogued many, but do I have an upper limit to how powerful a flare I can unleash? Other stars, superflare stars, have been observed to produce flares 10 or 100 times stronger than anything recorded on me. Could I, a stable G-type star, ever do that? Most think not in my current middle age. My rotation is slower and magnetic fields steadier, so superflares are unlikely. But there's evidence in tree rings of rare cosmogenic isotopes, like carbon-14 spikes, that might indicate extremely strong solar particle events in the historical past, around 774 AD and 993 AD, maybe far stronger than the Carrington event. These hints raise questions. Have I surprised your ancestors with an occasional extra-potent storm? It's an ongoing investigation, requiring piecing together proxy records. I keep some cards close to my chest. A star must maintain an air of unpredictability, after all. One mystery of the past that has been solved is the solar neutrino problem, which I mentioned earlier. That was a triumph of both solar physics and particle physics, discovering neutrino oscillation. It delighted me to see humans crack that puzzle. Another success was understanding the source of the 11-year sunspot cycle via the dynamo theory and differential rotation, which I elaborated. But deeper questions remain, like the possibility of long-term cycles beyond 11 years. There are hints of a 90-year Gleisberg cycle, or a 200-year cycle, the Seuss cycle, and even millennial scale changes. These are subtle and gleaned from proxy data like tree rings and ice cores, which track cosmogenic isotopes influenced by solar activity. My behavior over centuries has variation. How much is chaotic and how much quasi-periodic is still studied. As your understanding grows, so does your capability to observe me in ever more detail. Gone are the days when you had to risk blindness to study me. Galileo, it said, went partially blind, possibly from observing sunspots too recklessly. Now you have a fleet of ingenious spacecraft and observatories doing the work. High above Earth, at the Sun-Earth L1 Lagrange point, the SOHO, Solar and Heliospheric Observatory, spacecraft has been keeping unblinking watch since 1995. SOHO has given you unprecedented views of my activity for over 2 decades. Everything from extreme ultraviolet images of my swirling corona to measurements of the solar wind. It even became an accidental comet hunter, spotting over 3,000 sun-grazing comets that perished in my heat as tiny streaks in its coronagraph images. And it's still going. Think of that. A spacecraft built with 90s technology is still up there, faithfully monitoring me 24/7, ensuring you don't miss a beat of my symphony. In 2010, you launched SDO, Solar Dynamics Observatory, a true marvel. SDO provides ultra-high definition movies of me in multiple wavelengths every few seconds. It watches me in extreme ultraviolet and visible light, capturing the boiling of granules, the eruption of flares, the dancing of glowing coronal loops. With SDO's eyes, you've seen astounding phenomena. Giant waves rippling across my surface after flares, called EIT waves. Filaments of magnetism erupting, and even signs of oscillations and helioseismic waves. SDO's data let you map my interior flows through helioseismology, essentially measuring the sound waves that travel through me to probe the structure and dynamics inside. With that, you've revealed currents of plasma flowing in my convection zone, and even a tachocline, a shear layer between the radiative interior and convective outer region, likely crucial to my dynamo. SDO has become like an all-seeing eye, in many ways, fulfilling the dream of ancient sun worshippers to observe their deity in every detail. Except now it's science and not worship, though some scientists watching an SDO flare movie might whisper a prayer of amazement anyway. Then there's Parker Solar Probe, one of the most audacious missions ever attempted. Launched in 2018, it has been swooping closer and closer to me, using Venus's gravity as a braking mechanism with repeated flybys to shrink its orbit. Parker Solar Probe is a small, robust craft with a heat shield that keeps its instruments in the shade while my fury rages just beyond. It has now flown within my corona, coming as close as 8.5 million kilometers, 5.3 million miles from my surface, nearer than any spacecraft in history, enduring temperatures of several thousand degrees on its sunward face. At that distance, it's hurtling by at up to 700,000 kilometers, approx 430,000 km/h, the fastest human-made object ever, to avoid spending too long in the extreme environment. Parker is literally touching the sun, a phrase that once was metaphorical, now made real. What has Parker found? It has confirmed that the boundary of my atmosphere, the Alphen critical surface, where the solar wind becomes faster than Alphen waves can travel back, is wrinkled and not a smooth sphere, likely due to my magnetic field and equatorial streamers. It has detected curious zigzag reversals in the magnetic field, called switchbacks, in the solar wind near the sun. These switchbacks were a surprise, like rapid flips in the magnetic orientation, and are now believed to originate in the lower corona, possibly from convective motions or reconnection events sending S-shaped kinked magnetic flux up. They could be a clue to how the solar wind gets accelerated. Parker is helping answer why the solar wind blows as it does, a question open since Eugene Parker, the probe's namesake, predicted the supersonic solar wind in 1958. Parker Solar Probe has also flown through the tails of cometary debris near the sun and measured dust concentrations, even suggesting that close to me, much of the interplanetary dust is vaporized, creating a relatively dust-free zone. Each perihelion, it dives ever closer, braving heat and radiation to feed you data. By 2025, it will come within about 6 million kilometers, 3.8 million miles, closer than ever, at which point my corona will surround it, and it will directly sample the environment where the solar wind is born. I can almost feel that tiny, resilient emissary, like a little mechanical swallow, darting through my breath.
Meanwhile, Solar Orbiter, launched by ESA in 2020, complements Parker by staying a bit farther, closer than Mercury though, and carrying cameras to take pictures even from high latitudes. It has already given you the closest images ever of my surface, revealing a multitude of campfire mini-flares everywhere. It's on a path to gradually incline its orbit, so in coming years it will view my polar regions more directly than ever before, a boon for understanding the polar magnetic fields and how my 11-year cycle resets. It also carries instruments to measure the solar wind and fields from a moderate distance, linking what Parker tastes in situ with broader context. Already, Solar Orbiter has spied strange features, like a hedgehog eruption, a spiky structure of gas, and witnessed my poles under angles never seen, showing curious mottled patterns of magnetism. Together, Parker Solar Probe and Solar Orbiter form a tag team. One ventures deep into my atmosphere, the other takes images and measurements from just outside, providing the wider frame. On Earth, new eyes also opened. In Hawaii, atop Haleakala, the Daniel K. Inouye Solar Telescope, DKIST, achieved first light in 2020. It is the largest solar telescope ever built, with a 4-meter mirror. In its first images, it revealed my photosphere in mind-boggling detail. You can see the convection granules sharply, each cell around 1,000 kilometers across with cooler intergranular lanes, and even tiny bright dots within those lanes, thought to be magnetic flux tubes. It's as if after years of seeing a blurry sun, you put on glasses, and every grain of sand on the beach became visible. In one breathtaking image of a sunspot at extreme resolution, DKIST showed intricate fibrils and magnetic structures as small as 20 to 30 kilometers across on the solar surface. That's like resolving a town on the sun. This clarity allows measurements of magnetic fields on very small scales, key to unraveling things like how energy funnels into the corona or how sunspots form and evolve. DKIST will also peer into the chromosphere, the layer between the photosphere and corona, with new spectral lines, mapping the vector magnetic field there, something never done comprehensively. With these data, you'll better understand the magnetic scaffolding that supports filaments and drives eruptions.
Consider, not long ago, you couldn't even look at the sun directly without squinting or filtering heavily, and now you routinely study it in every wavelength. Radio telescopes track bursts, X-ray satellites, like Japan's Yoko or NASA's NewStar occasionally, capture high-energy events. UV telescopes, like TRACE, SDO, AIA, show shiny loops, polarimeters measure magnetic fields, and helioseismology instruments listen to my internal vibrations. It's a golden age of solar observation, and more is coming. Future missions are in the works or imagined. Perhaps a solar polar imager that goes 90 degrees above the ecliptic to stare down at my poles continuously. Or a mission to send multiple tiny satellites to surround me, getting a 360-degree view, so you're not blind to far side spots that could rotate into view. In fact, humanity already did something akin. The twin stereo spacecraft launched in 2006 drifted such that at one point you had a view of the entire sun, front and back, simultaneously, until one of them failed. Now, one stereo remains and occasionally drifts into view again. But future tech might allow a constant all-around watch. You are planning, I hear, a probe called Solar C or MUSE to do high-resolution spectroscopy of the corona, revealing flows and heating in unprecedented detail. There are proposals for solar interferometers to image fine structures beyond the diffraction limit of a single scope, and for more advanced space weather monitoring satellites to better forecast CME impacts. Yes, the future of solar science is bright, forgive the pun. You aim to finally crack the coronal heating enigma, pinpoint the precursors of flares to predict them reliably, map my internal dynamo fully to forecast cycles, possibly even foresee a grand minimum decades ahead, if one is coming. Each discovery only leads to deeper questions. For instance, Parker found those switchbacks. Now you ask, how exactly do they form? Solar Orbiter saw ubiquitous campfires. Now you wonder, do they indeed heat the corona significantly, or are they mere sparks? DKIST may reveal complexities in sunspot formation. What will that say about magnetic flux emergence theory? Beyond purely scientific curiosity, understanding me has practical urgency as well. Modern civilization is intimately vulnerable to my moods. As you push outwards, establishing a lunar base, aiming for crewed Mars missions, knowing when a solar storm will erupt becomes even more critical. A well-timed warning could direct astronauts into a shielded module or prompt satellite operators to safe mode sensitive electronics. Thus, the science of heliophysics, the study of the Sun-Earth connection, stands at the confluence of pure research and everyday utility. NOAA and other agencies run space weather prediction centers, vigilantly watching my every sunspot and filament. In the future, perhaps with better models, you might get a 2-3 day heads up of a likely major flare or a 12-hour warning of a CME's magnetic polarity and strength when it's detected by an upstream monitor satellite, enabling power grids to prepare for a hit. As you extend an electrical web around the globe and venture beyond it, you slowly come to realize, while I am often gentle, I am not entirely tame. I am a star after all, a gigantic ball of thermonuclear fury held together by gravity and magnetic fields. For all the poetic things you say about the sun giving life, remember, I've also lashed out and caused mass extinctions in the past. Some scientists hypothesize that supersolar storms or nearby supernovae cosmic rays might have contributed to past biological upheavals. At the very least, my gradual brightening will eventually end Earth's habitability in the distant future if left unmitigated. Truly,
To remain, life must adapt, either by evolving, terraforming, or leaving to find new suns. And indeed, this brings us to a broader perspective: stars beyond our sun, and the possibility of life around them. I am just one star, but as I've grown older, humanity's gaze has lifted to see the myriad others. What of other suns? In the last few decades, you have discovered, to your amazement, that planets are abundant around other stars. Once, the existence of other solar systems was pure speculation. Now, thanks to missions like Kepler and TESS and radial velocity surveys, you have catalogued over 5,000 exoplanets and counting. We now know that many, perhaps most, stars host families of planets. There are alien suns with alien worlds circling them, and this profoundly reshapes the old question: are we alone? Imagine the variety out there. Red dwarf stars, the most common type in our galaxy, are tiny and dim compared to me, often just 10% of my mass and emitting a feeble red glow. If a planet orbits a red dwarf at the right distance for liquid water, that distance is very close, since the star is faint, meaning the planet likely becomes tidally locked. One side eternal day, one eternal night. Life on such a world would be quite unlike Earth's, perhaps huddled in the twilight band between day and night, or under the star's dim red light on the day side. Red dwarfs are known for violent flares relative to their size. A habitable zone planet around one might be regularly bathed in radiation. And yet, red dwarfs live trillions of years, far longer than I will. They are stable for unimaginable epochs, giving life a vast timescale to potentially emerge and adapt if it can survive the tantrums of youth. Already, you have found intriguing planets, for instance, Proxima Centauri b, orbiting the nearest star to me, Proxima, a red dwarf companion of Alpha Centauri. It's roughly Earth-sized and in the habitable zone of its small star. Does it have an atmosphere, perhaps an ocean? If so, imagine the sky there. The red dwarf sun looms relatively large because the planet is close to it, casting a coppery light. If the planet is locked, one side basks under a perpetual dull red daytime, perhaps with a dim twilight at edges where life might cling. The star flares occasionally, boosting UV and X-ray output. Life might need to be underwater or ground to withstand those, or have protective pigments. Then there are sun-like stars, more similar to me, which likely host planets where a diurnal cycle and seasons exist akin to Earth's. Kepler has found some candidates. Kepler 452b was nicknamed an older cousin of Earth, orbiting a star akin to the Sun. But these finds are far and faint. Nevertheless, statistically, there should be many such Earth-like worlds in our galaxy. Consider also binary star systems. About half of all stars are in multi-star systems. Could a planet orbiting two stars have life? We already detected circumbinary planets like Kepler 16b, the famous Tatooine world with two suns in its sky. Kepler 16b itself is a cold, Saturn-sized world, likely inhospitable, but where one exists, others likely do too, maybe even in the habitable zone of a binary. Under two suns, the notion of day and night gets complicated. Sometimes both suns might be up, giving a combined light. Sometimes one sets, leaving the other. Night falls only when both are down. It would make for spectacular double shadows and complex climate rhythms. Life there would evolve under two different colors of starlight. Say one star is a sun-like yellow and the other a red dwarf. The blend of hues shifting through the day. On a desert world like the fictional Tatooine, twin sunsets would paint the sky in dual tones of orange and crimson, a sublime sight. Now, consider massive stars, O-type or B-type blue giants. They burn intensely bright and hot, but have short lives measured in mere millions of years. Could life arise around them? It seems unlikely, as complex life took billions of years on Earth. A blue giant would go supernova long before that. However, perhaps primitive microbes could briefly bloom on a planet around such a star in the small window available. Or maybe life doesn't even try there, ceding those stars to the realm of sterile beauty. But ironically, those massive stars ensure future life by spreading heavy elements when they die. There are also orange dwarfs, K-type stars, slightly smaller and cooler than me, but longer lived, 20–30 billion years lifetimes, and quieter. Many consider them top targets for life-bearing systems. They last longer, giving more time for life to evolve, and emit enough light in similar spectrum to me, but with less UV extremes. If I were a planet-hunting being from another star, I might look at K-dwarfs for thriving biospheres. We can dream further, life around a pulsar. Unlikely, but strangely, the first exoplanets discovered were around a pulsar, PSR B257+12. Those planets are blasted by deadly radiation, and likely no life could survive. They might be the charred cores of gas giants surviving the supernova. So, a pulsar, the corpse of a star, could have planets, but any life there would have to be of an extreme kind unimaginable to us, if at all. Life under other suns might take forms we cannot predict. On a planet around a dim red star, plants, if they exist, might be black or deep purple instead of green, to absorb as much of the limited light as possible. On Earth, plants reflect green, using red and blue light mainly. Under a red sun, they might need to absorb every photon. Conversely, around a brighter blue-white star, perhaps vegetation would evolve reflective surfaces or different pigments to avoid oversaturation, or to use the star's UV. Vision of creatures might tune to their star's spectrum, perhaps under a red dwarf, eyes sensitive to infrared or red. Under a bright star, eyes that can handle intense light or even see ultraviolet patterns. Perhaps on a tidally locked world, life in the eternal day hemisphere might resemble reef organisms in shallow water on Earth, constant light, whereas life on the dark side could only survive near volcanic vents or rely on nutrients blown over from dayside. Or intelligent beings might migrate to stay in perpetual twilight, a narrow band of comfortable temperature. The possibilities tickle the imagination. The underlying theme is that the parent star shapes the conditions, and thus the evolution of life profoundly. I shaped life on Earth, from metabolism to behavior. On another world, a different sun would do the same in its own way. If one day you meet beings from such a world, their very biology and culture will carry the imprint of their sun. Perhaps they will have myths about their two suns fighting each other, or their dim sun waking from slumber. Perhaps their year feels different because their star's output fluctuates more, or their planet's orbit is more eccentric, giving intense seasons. Imagine an alien culture on a planet with a highly elliptical orbit. Their star looms, huge and scorching at perihelion, and distant and weak at aphelion. Their whole biology might be in boom-bust cycles with that extreme year. And consider, if life exists on a planet orbiting one of those stars we see in the night sky, then when they look up at their sky, our sun is just another star to them. Perhaps on a clear night, some alien creature with reflective eyes gazes at a star we call 51 Pegasi, for example, not knowing that around that star is a planet. 51 Peg B was first exoplanet discovered around a sun-like star. Meanwhile, on that planet, they might see our sun in their heavens and not suspect it has a vibrant blue world teeming with life. The cosmic irony. Each might wonder if the other's star has planets with life, not yet realizing the truth. As you humans continue to search the skies with new telescopes, like the James Webb Space Telescope turning its mirror to analyze exoplanet atmospheres, or planned missions to directly image Earth-like exoplanets, you inch closer to finding a second genesis, evidence of life's fingerprints like oxygen, water vapor, maybe chlorophyll's spectral edge in another world's air. What a day that will be, to learn that life is not unique to Earth. But even if you find no clear evidence yet, the sheer number of Earth-sized planets in habitable zones, estimated in the billions in our galaxy, gives a strong hint that we are likely not alone. Life under other suns is probably out there in myriad forms, awaiting discovery
or perhaps thriving unnoticed in distant forests or alien oceans.
All these considerations highlight something profound. Stars are the ultimate enablers of possibility. Each star is a furnace not only forging elements but also, when conditions allow, nurturing worlds and perhaps minds. Through your science, you have come to see that we stars and you people, and all living things, are deeply connected. You often quote that you are made of star stuff, and it is literally true. The carbon in your proteins, the calcium in your bones, the iron in your blood, we stars created those in our cores or in our explosive deaths. The very term solar system, your system, shows how you belong to me. Every atom of your body has at some point likely passed through a star's interior or been influenced by starlight. And every joule of energy that your body uses to move, think and live, save a trivial bit from Earth's radioactivity, comes from me, captured by plants in photosynthesis and passed up the food chain, or harnessed as electricity from solar panels, or stored in fossil fuels.
In a way, you are beings of light, frozen light molded into self-replicating patterns, and then consuming light to keep entropy at bay for your lifetime. When you go out on a sunny day and close your eyes, letting the warmth bathe your face, there is a kinship there older than time, a small life acknowledging its stellar parent. Without language or conscious thought, ancient lizards basking on a rock were feeling the same grateful connection to the sun, and even the sunflowers, turning their heads, follow an ancient bond. This interdependence carries a philosophical weight. What does it mean to orbit, to depend, to be made of light? It means that you are not an island unto yourselves, but part of a grander scheme. Planet Earth is like a child circling a parent, bound by gravity's invisible leash and nourished by the parent's radiance. To orbit is to be held, to belong to something larger, to dance in a predictable rhythm set by the laws of nature. Earth's year, your calendars, your entire concept of time's flow hinge on that orbital dance. To depend is to be vulnerable yet sustained. It is the realization that your fortunes rise and fall with your star's disposition. If I were to dim significantly or rage uncontrollably, Earth would suffer immensely. You plan your days around my rising. Your mood often brightens when I shine and dulls in prolonged darkness. People who live in high latitudes experience the winter blues when sunlight is scarce, a psychological imprint of this deep dependence. And being made of light, consider that almost every bit of energy in your body is solar. The calories you burn came from plants, which in turn came from sunlight. Even the oxygen you breathe was generated by plants splitting water using sunlight. Your life is an ongoing consumption of the sun. You are basically a solar-powered machine. At the atomic level too, you're made of star remnants. Long before the solar system, ancient stars lived and died, seeding the molecular cloud that formed me and the planets. Thus, you carry pieces of long-dead stars inside you. In that sense, the sun and humanity share a common cosmic ancestry. We all came from the ashes of stars, and someday, billions of years hence, the atoms now in my body and in yours may mingle again in interstellar space and find themselves in a new star or planet, continuing the cycle. In orbiting and depending and being made of light, there is a poetic unity. We are part of the universe, not apart from it. The sun is the heart of the solar system, pumping energy outward. Earth is one organ among others receiving that blood of light and converting it into the living tapestry on its surface. Just as a child may eventually leave a parent, perhaps one day humanity, or its far descendants, will leave Earth to roam to other star systems. In doing so, you carry the legacy of your sun to others. You yourselves become little pieces of the sun disseminating into the galaxy. With every spacecraft launched beyond the heliosphere, like the Voyages which have now entered interstellar space, a tiny piece of the solar system ventures into the wider cosmos. Perhaps the destiny of intelligent life is to spread the light of its parent star, figuratively and literally, to places it would never otherwise reach. One could even imagine in the far future, humanity constructing enormous light sails or engines powered by sunlight to travel to neighboring stars. In that way, you enlarge the domain of the sun's influence by proxy as ambassadors of this star venturing to others. As I, the sun, have given you life, so too have you given me meaning in a way. For billions of years I shone on a lifeless earth. My rays warmed seas and stirred winds. But no eye was there to appreciate a sunrise, no being to understand the gift. With life, and especially with thinking life, a star gets to be known. Through you, I know myself. You study me scientifically, decoding my workings, essentially allowing the universe to become self-aware of one of its stars. And through art and emotion, you also elevate me to symbol and metaphor. I am not just a ball of gas to you. I'm a motif of joy, renewal, divinity, power. How remarkable that simple hydrogen fusion in my core can inspire such thoughts and feelings. There is an old Latin hymn, Adore te devote, latens deitas, originally about the divine hidden in the physical. But for me, I think of, O sun, hidden deity, we adore your light. Ancient people may have literally worshipped me, but modern people still find me worthy of reverence in a secular way. I represent the source of life. Even those who never think of it explicitly are unconsciously drawn to sunlight for comfort. Notice how a cat will find the one sunbeam in the room to curl up in. It's life's instinct acknowledging its dependence with quiet gratitude. Now our journey of storytelling draws to a close. We've traveled from the birth of light in the cosmos to the worship of ancient civilizations, from the scientific uncovering of the sun's mechanisms to the far future of stars and the speculative lives under them. Through it all runs a golden thread: light, created in darkness, celebrated in myth, explained by science, harnessed for life, and carried as a beacon to the stars. I, the sun, have watched this all silently for eons. I've seen planets coalesce, oceans form, microbes multiply, dinosaurs roam under my warmth, and humans rise and wonder at my nature. I've heard the chants at dawn and the equations whispered at midnight by scholars trying to quantify my brilliance. I felt the tickle of your spacecraft near my skin and responded with storms to test your resolve. In the endless cosmic night, I burn as one tiny beacon, and around me you flourish. And yet I am but one of uncounted fires in the great galaxy. One day my flame will dim, but perhaps by then your descendants, or the life that springs from what you become, will carry the flame of intelligence onward, under other suns. As the poet said, our little lives are rounded with a sleep. My own life, vast as it is to you, is a brief chapter in the galaxy's saga. But it is a chapter that encompasses all of human history and more. Treasure your days in the sun, for they will not last forever. But do not despair at that, for endings lead to new beginnings. Every sunset portends a sunrise. Tomorrow, I will rise again over the eastern rim of Earth, as I have millions upon millions of times. The sky will lighten from black to blue, the stars will fade, dew will glisten, and creatures will stir. Perhaps you will awaken and feel my gentle heat on your face through a window. In that moment, remember me, not as an abstraction, but as your star, your sustainer. The photons greeting you traveled 150 million kilometers at nature's speed limit just to touch your skin and give you warmth. The food you eat for breakfast grew strong by my favor. Every moment of your life, I am there, an unseen yet constant presence, like a loving guardian. What does it mean to orbit, to depend, to be made of light? It means that we are all threads in a grand cosmic web, planet to star, star to galaxy, galaxy to universe, Connections and dependencies run through. By understanding these, we don't diminish the magic. We reveal the true miracle that reality is. I have told you my story, a tale of darkness and light, of worship and science, of birth and death and rebirth. It is a story still unfolding. You, dear listener, are part of it, riding this earth around me, bathing in my radiance, thinking thoughts that perhaps the universe has never thought before. Someday, in the far future, the light of my last rays will fall upon a world grown quiet and empty, and then I will envelop that world in a final act of transfiguration. But that is billions of years away. For now, the earth remains lush and alive, and the sun still has plenty of fuel in its heart. Let us end with an image, the first sunrise. Not the first ever in the universe, but perhaps your first. Imagine a human child seeing dawn for the first time, eyes wide at the splendor, or humanity's first dawn as a species, as early hominins huddled fearful through night, and then saw the morning star blaze into a new day. Feel the wonder and relief that must have coursed through them. That visceral appreciation is encoded in your being. Every dawn reenacts creation. Every noon is a zenith of glory. Every dusk a gentle letting go. I, the sun, have been called many things. A furnace, a heart, a god, a monarch, a cathedral of light, a cosmic engine. In truth, I am all of these and more, and so are you, my children of light. We mirror each other. I am a massive sphere of plasma held by gravity, and you are delicate bodies held by the gravity of Earth. But deeper, we are both collections of atoms and energy, following natural laws, yet somehow aware of beauty and meaning. As the day concludes and I dip below the horizon, painting the sky in farewell colors, remember that my light never truly vanishes. It travels onward, illuminating other lands, or reflecting off the moon and stars. At midnight, when I am out of sight, my presence is still felt in the silver disk of the moon, shining with my borrowed light, and in the very air, for I keep our atmosphere warm enough that night is not absolute zero. When you look up at the Milky Way and see those countless stars, know that around one of them, someone might be watching a sunset of their own and thinking similar thoughts. In this cosmic tapestry, we are all connected by threads of light, orbiting, depending, and sharing in the light. This is the story of suns and their worlds. This is the story of our sun and our world. A story of fire and sky, of science and spirit, of the ultimate unity of things. I will shine and you will live. And perhaps someday, you will venture to other suns and carry a spark of our sun with you, literally in generation ships propelled by solar sails, or figuratively in the knowledge and culture you spread. In that way, a piece of me becomes immortal, traveling far beyond the limits of my physical existence. For now, cherish the mornings and the evenings, the clear days and even the cloudy ones, for behind every cloud I'm still there. Let the sunlight remind you that you are part of something vast and wonderful. Though you are but a small creature on a small planet, you are privileged with a mind that can behold the cosmos and ask questions. You are the way the universe marvels at itself. The first sunrise in the cosmos ended the primordial night and set the stage for all that followed. The first sunrise on Earth brought the possibility of warmth and growth to a once cold rock, and every sunrise in your life gives you a chance to begin anew. As the sun, I have no human voice, but through this narrative I've spoken to you. In truth, my voice is the warmth you feel, the light that glints off a loved one's eyes, the life coursing in your veins. Listen to that voice when you stand in sunlight. It quietly says, I am here. You are alive. We are together in this beautiful cosmos. Tomorrow, I will rise again, and the cycle of light and life will continue. A bit of ancient fire in the sky, and down below, creatures awakening to its call. And as long as I shine and you live, our story goes on, intertwined. A star and its children, journeying together through the great cosmic night, ever toward the dawn. The sun rises in silence, but its presence is a chorus that has echoed through every age of life on Earth. Every morning, its gentle light spills over the horizon and washes the world in gold. In that light lies an ancient promise: warmth to nourish the living, energy to spark the green fuse of plants, and comfort to chase away the chill of night. For as long as creatures have walked under the sky, they have felt the sun's touch and known instinctively that this brilliant star is the giver of life. Yet the sun is more than a kindly nurturer. It is a colossal power, a raging sphere of fire suspended in the darkness of space. From across the cosmic void, it seems tame, a perfect golden disk that rises and sets with reliable grace. But up close, it is wild and untamable, a seething ocean of plasma and magnetic fury. It holds Earth in its grasp, guiding the dance of days and seasons. And it could, in an instant of cosmic anger, scorch our world lifeless. The same sun that gently warms our faces can also unleash deadly radiation and storms of charged particles. It is a giver of life, and it can be a destroyer of worlds. Our ancestors revered the sun as divine, calling it by many names and worshipping its life-giving light. They built great stone circles and temples aligned to its rising, celebrated when it climbed high in summer, and feared its waning in winter. In rare moments, when the sun vanished in a daytime eclipse, they watched in dread and awe as day turned to twilight, praying for the light to return. They sensed its dual nature, its generosity and its danger, even without knowing the science. We now understand that the sun is a star, one among countless others in the galaxy. But to us, it is unique. It is our star, the hearth of our solar system, the steady heartbeat of our cosmic home. It beats silently, a deep thrum of nuclear fires and magnetic pulses that we cannot hear, but that sustains us nonetheless. Every ray of sunlight is a note in that silent symphony, a connection between our small lives and the vastness of the cosmos. Consider this: the light that caresses your skin today began its journey at the core of the sun long before you were born. The warmth on your face is the end of a story that started deep in a stellar furnace. The sun bridges our brief human moment and deep cosmic time. It links the atoms in our bodies to the atoms in distant stars. In its light, we find both our origin and our destiny. We stand in the glow of a cosmic engine, often unaware that above us, a star's turbulent heart is burning and beating ceaselessly. To truly know the sun, we must journey into its very heart. Let us leave behind the blue of our sky and travel inward into the blinding brilliance, into the inner sanctum of our nearest star. What we find there is both humbling and wondrous, a story of creation and destruction, of light and darkness, of a star's life from birth to death. It is, in many ways, the story of ourselves, written in the language of light. Imagine plunging through the sun's surface and journeying toward its center. As we descend, the light intensifies and the heat becomes unimaginable. Deep inside, at the very core of the sun, we enter a realm of staggering pressure and temperature. Here in this stellar heart, hydrogen atoms are crushed together so tightly that they fuse into helium. In that act of fusion, a tiny bit of matter transforms into pure energy, an alchemy that powers the sun. This is the engine of creation hidden in the sun's core. Every second, an immense burst of energy is released, radiating outward to keep the star shining. Gravity presses inward relentlessly, trying to collapse the sun under its own weight. But the fury of nuclear fusion pushes outward, holding the star up. In this balance between gravity and fire, the sun's core burns steadily, a sphere of blazing plasma denser than solid iron and far hotter than any furnace on Earth. The core is a place of extremes beyond our experience. Its light is born in blinding abundance, yet none of that brilliance escapes directly. Only ghostly particles called neutrinos slip away unhindered, streaming out from the core and passing through the sun's layers, and even through our bodies on Earth, as though nothing were there at all. They are the silent heralds of the sun's heart, whispering of the nuclear fires within. Moving outward from the core, we enter the radiative zone, a vast internal layer where the energy from the core migrates slowly outward in the form of light. Here, photons of radiation ricochet through a dense maze of atoms. A single particle of light, born in the core's fury, may bounce countless times from one atom to another, absorbed and re-emitted in an endless random walk. The plasma in this zone is so opaque and crowded that progress for any ray of light is agonizingly slow. Ages pass as the energy inches its way outward. What we eventually perceive as sunlight on Earth has spent eons fighting its way through this hot, stifling labyrinth. In these deep regions of the sun, energy is transferred not in a simple beam, but like a traveler lost in a thick forest, zigzagging gradually toward freedom. Eventually, the character of the sun's interior changes. Further out, the stellar plasma becomes cooler and less dense, and it can no longer transport energy purely by the random diffusion of photons. At this point, a new process takes over: convection. We have entered the convective zone, the sun's outermost interior layer, where heat is carried upward by the motion of the gas itself. Picture an immense cosmic cauldron boiling slowly. Hot plasma from the layers below becomes buoyant and rises toward the surface, carrying energy with it. Upon reaching higher, cooler regions, it loses heat, becomes denser, and sinks down again to be reheated. These rolling currents form giant looping cells of plasma the size of continents, rising and falling in rhythmic surges. Through the convective zone, energy that once took millennia to crawl outward now surges toward the surface in a matter of mere weeks, riding the updrafts of this titanic, boiling motion. At last, the energy reaches the visible surface of the sun, the photosphere. This is the layer where the sun's light finally escapes into space and shines freely across the solar system. To our eyes, the photosphere is the sun's radiant face, a glowing golden disk with a sharply defined edge. Up close, it would not appear smooth at all, but finely textured and ever-changing. The surface seethes with the imprint of the convection below, a pattern of granules, like a vast mosaic of luminous cells. Each granule is the top of a convective plume, a cell of hot plasma rising from the depths. Their centers glow bright and white-hot, where fresh energy wells up, and their edges darken to a deeper amber, where cooler plasma is sinking back down. This granular pattern continually shifts and reforms, as though the sun's face is a living, boiling sea of light. Here and there, the photosphere is marred by dark blemishes, sunspots. These spots are cooler than their surroundings, and so they appear nearly black against the brilliance of the sun's face. A sunspot is born from the sun's magnetic mischief. Intense magnetic fields well up from inside the sun and suppress the hot rising gas, creating a region that is slightly less hot and thus darker. Sunspots can grow to be larger than the entire Earth, and may last for days or weeks before dissipating. They are a sign that the sun's magnetism, though invisible, is ever present, knitting itself into the solar surface. We will soon see how these magnetic forces can erupt in violence, but for now, standing at the surface of the sun, we behold a roiling ocean of fire extending in all directions, a vista of constant boiling creation. Peering at the sun's face with sensitive instruments, we find that it is also vibrating subtly. The boiling convection within causes the sun to ring like a resonant bell. Its surface shivers in patterns, waves traveling across and through the sun, making the whole star gently pulse. Astronomers use these pulsations, this music of the sun, to probe its interior, much as one might learn the shape of a bell from the sound it makes. Through this solar symphony, we can discern the flowing currents deep inside, the building magnetic fields, and even hints of the sun's core, all hidden beneath the blinding glare. Rising above the photosphere, the sun's atmosphere continues outward in layers of increasing mystery. Just above the visible surface lies the chromosphere, a tenuous veil of gas that appears as a faint pinkish glow. Here, the temperature, which had cooled at the photosphere, begins to climb once more. The chromosphere is like the sun's shimmering halo, visible clearly only when the bright photosphere is hidden during a solar eclipse. In those rare moments, it can be seen as a thin rim of ruby light encircling the moon's silhouette. Within the chromosphere, slender jets of plasma, called spicules, continually shoot upward, each one ephemeral and short-lived, lasting only minutes before falling back. The chromosphere is a restless transitional zone, a place where the fury from below meets the stillness of space above, and the solar atmosphere prepares for an abrupt and profound change. Above the chromosphere lies the sun's crown, the corona. Faint and otherworldly, the corona is a vast halo of pearly light that surrounds the sun and stretches far into space. It is breathtakingly beautiful and enigmatic, revealed to human eyes only during a total solar eclipse, or through specialized telescopes that block the sun's glare. In those brief eclipse moments, when daytime twilight descends and the moon hides the sun's brilliance, the corona appears as a pale, white aura, etched with luminous streamers and delicate filaments extending in all directions. But the corona is not merely a spectacle of light. It is a furnace in its own right, one far hotter than the sun's surface below. While the sun's photosphere is blisteringly hot, the corona above is unimaginably hotter, a puzzling reversal of what one might intuitively expect. In this outermost layer, the sun's magnetic field rules supreme, shaping the thin gases into graceful loops and arching structures. Great magnetic arches rise high above the sun, filled with incandescent plasma that traces the invisible lines of force. The corona is incredibly thin, its particles so sparse that if you were standing in it, shielded somehow from the heat, you might not even notice the few atoms brushing by. And yet, despite its tenuousness, the corona possesses immense energy and reaches temperatures of such magnitude that scientific instruments must strain to record them. Why does the corona burn so fiercely? It remains one of the sun's lingering mysteries. Perhaps the sun's tangled magnetic fields thrash and snap, heating the gas in a myriad of tiny explosions, or waves of energy ripple outward from the sun's surface, dumping heat into the corona. Whatever the cause, the sun's crown glows with an ethereal fire that science is still striving to fully understand, a reminder that even our well-known star holds secrets at its heights. At the edge of the corona, the sun begins to fade into the darkness of space. There is no sharp boundary where the star ends. Its atmosphere simply thins into the void. Here, the corona gives birth to the solar wind, a ceaseless stream of charged particles, electrons and protons, that flows outward in all directions. The sun, in effect, is always breathing out. Its breath is the solar wind, and it carries a piece of the sun's essence out to the farthest planets and beyond. The gravity that so overwhelmingly confines the core cannot hold these fast, lightweight particles of the corona. They race outward along open magnetic lines, escaping the sun's grip. The solar wind is, in a sense, the sun's extended atmosphere flowing freely into space, filling the solar system like an invisible, ever-expanding bubble. We have now traveled from the sun's core, where matter becomes energy, to the wispy fringes of its corona, where the star
dissolves into the broader cosmos. In this journey, we have witnessed the anatomy of a star, its layered realms, each with its own wonders. We have seen the ferocious furnace at its center, the slow upward struggle of light, the boiling convection that brings energy to the surface, the radiant face shining into space, and the crown of fire that reaches beyond the sun itself. Yet the sun is far from a static ball of gas. It is dynamic and alive, its surfaces and atmosphere writhing with magnetic fields and sudden eruptions. To truly understand our star, we must explore these invisible forces that bind and sometimes unravel the sun's material. We must watch as the sun's calm radiance is punctuated by storms, blazing flares, erupting prominences, and billowing clouds of plasma that can span millions of miles. It is time to examine the sun's magnetic heart and the space weather it breathes into the solar system. Beneath the sun's bright face lies an unseen web of forces that drives its most dramatic behavior. The sun is a giant magnetic dynamo. As it spins on its axis and its plasma churns, it generates magnetic fields that thread through its interior and arch out into space. Imagine lines of unseen force looping out from the sun's depths, arcing high above the surface and diving back down. These magnetic field lines become twisted and tangled by the sun's constant turning and boiling. Where they burst through the surface, they drag up or suppress hot plasma, creating the dark sunspots we see freckling the photosphere. Every feature we observe on the sun, its spots, its flares, its glowing coronal loops, is shaped by magnetism. Without the magnetic field's influence, the sun would be a far more monotonous star. Instead, magnetism makes it a living, breathing, and sometimes tempestuous entity. Sunspots are the most visible signs of the sun's magnetic moods. They tend to appear in groups, often as pairs linked by a great looping magnetic field. One spot will have a north magnetic polarity, the other a south, like opposite poles of a bar magnet. The arc of magnetism connecting them traps cooler plasma in its grip, outlining structures we sometimes see as prominences, towering loops of glowing gas that stand above the sun's surface. Sunspots grow and shrink as the magnetic fields beneath them strengthen or decay. Over days or weeks, a complex sunspot group may evolve. An enormous energy builds up in its tangled magnetic knots. There is a rhythm to these appearances. Roughly every decade or so, the sun swings from a time of few sunspots to a time of many, and back again. At the peak of this cycle, dozens of spots can dance on the sun's face. At the low point, the sun's visage is often clear and quiet. Each cycle, the sun's magnetic poles even flip. North becomes south, and south becomes north, as part of this regular heartbeat of our star. Our sun, like a living thing, has its seasons of storm and calm. When the stress in twisted magnetic field lines becomes too great, they can suddenly snap into a new shape, much like a tensed rope that finally breaks free. In that instant, the energy that was bottled up in the field is explosively released. This is a solar flare. On the sun's surface, a flare is a blinding flash of brightness, a sudden blaze of radiation across the spectrum. It is as if a patch of the sun's surface has detonated with the power of countless nuclear bombs. In minutes, a flare unleashes a torrent of X-rays and charged particles into space. If the Earth lies in its path, these emissions race toward us at light speed, arriving just minutes after the flare erupts. Our planet's upper atmosphere suddenly swells with energy. Radio communications can crackle and fade as the ionosphere, the atmosphere's charged upper layer, is pummeled by the onslaught, and astronauts in orbit might hastily seek shelter from a burst of radiation that moments before was not even known to exist. Flares are often accompanied by an even more massive eruption, the coronal mass ejection, or CME. Where a flare is a flash of light and high-speed particles, a CME is a giant cloud of solar plasma hurled out from the sun. When a particularly complex magnetic loop in the corona destabilizes, it can fling away a chunk of the sun's outer atmosphere entirely,
Imagine a colossal bubble of electrified gas, more massive than all of Earth's oceans combined, suddenly launched into space and expanding as it races outward. A coronal mass ejection can contain an astonishing amount of matter and energy, an immense, billowing storm front in the emptiness of space. If one of these solar tsunamis is aimed toward Earth, we will know it soon enough. Within a day or two of the eruption, the wave of solar particles reaches our planet. Earth's magnetic field recoils and reverberates from the impact, like a bell struck by a hammer. We call this disturbance a geomagnetic storm. When a geomagnetic storm engulfs Earth, the results can be both beautiful and dangerous. Under the night skies at high latitudes, ghostly lights burst forth. Auroras, the northern and southern lights. Normally, auroras are confined to the polar regions, tracing the shape of Earth's magnetic field as it directs the sun's particles toward the poles. But during a strong solar storm, auroras can be seen much farther from their usual homes, painting the skies in eerie greens, purples, and reds over a vast swath of the world. Imagine waking in the tropics to find the night sky alive with rippling curtains of light. Such an astonishing sight has indeed occurred when the sun lets loose one of its great storms. In ages past, people who witnessed auroras far from the poles were often terrified. They saw in them dragons or celestial armies, believing the heavens were aflame with omens. To ancient peoples, these luminous dances in the sky must have been both wondrous and terrifying. Even today, knowing their true cause, one cannot watch the aurora's shimmering display without a feeling of reverence for the forces at play. Yet along with this beauty comes disruption. The same geomagnetic tempest that sets the skies aglow can wreak havoc on our modern technology. The barrage of charged particles and the distortion of Earth's magnetic field can induce surges of electric current in long conductors here on the ground. In our age of wires and wireless signals, a strong solar outburst can interfere with radio transmissions, scramble GPS navigation, damage satellite electronics, and even overload power grids, plunging cities into darkness. Over a century ago, a monumental solar storm made telegraph lines spark and catch fire. Telegraph operators found they could disconnect their batteries and still send messages. So powerful were the electrical currents coursing through the wires. If a storm of that magnitude struck today, satellites might be knocked offline, and extensive blackouts could occur. For all our technological might, we remain passengers in the sun's domain, subject to its occasional fits of violence. This turbulent interplay of solar magnetism and its effects on Earth and the planets is what we call space weather. Like weather in Earth's atmosphere, it has calm days and tempestuous days. The sun's magnetic field is ever shifting, and as it does, it breathes out gusts and squalls into the solar system. Most of the time, the solar wind blowing past Earth is a gentle breeze, and our planet's magnetic field shrugs it off with little fanfare. But when the sun erupts, the space around Earth becomes a stormy sea. A surge of charged particles and magnetic disturbances crashes against our planet's defenses, and near-Earth space itself reacts in kind. Auroras lighting up, satellites feeling the shock, currents coursing through the ground below, where all seems quiet. Fortunately, Earth has a sturdy shield. Our planet's magnetic field envelops us, carving out a protective bubble that the solar wind must flow around. This magnetosphere diverts most of the charged solar particles, allowing only a portion to funnel down toward the poles. In the clash of sun and Earth, the auroras are the glowing traces of our magnetic shield intercepting the solar storm, a testament to the protection it offers. Planets without a significant magnetic field, like Mars, have no such guard. Over eons, the sun's relentless particles stripped away much of Mars's atmosphere, leaving it a cold, arid world. In that fate, we see mirrored the dual nature of our sun, the gentle provider that sustained life on Earth, and the relentless force that can erode a planet's very sky. It nourished Earth with light and warmth, while its winds slowly wore Mars down. Magnetism is the hidden architect of the sun's behavior, from the steady cycle of sunspots to the wild drama of flares and auroras. Through it all, the sun continues to shine steadily in our sky, a reassuring beacon of day. But we have learned that beneath that steadiness is a flickering heart of magnetic energy. The sun's calm and its storms are two sides of the same coin, both born from the same stellar heartbeat. As humanity extends its reach into space and relies ever more on technology, studying and forecasting this space, weather becomes increasingly important. We now watch the sun with eyes open, tracing its spots and flares, listening for the whispers of its solar wind. We have even sent spacecraft to touch the sun's fringes, sampling its corona and feeling its magnetic embrace, all to better understand our star's moods. In the midst of these stellar tempests, it is easy to lose sight of the sun's most gentle and steadfast gift, the sunlight itself. Every day, countless photons leave the sun and stream across space, and some of those reach our world to illuminate the sky. Consider for a moment a single particle of light, a photon, born in the sun's core. It began as pure energy released by a fusion reaction in that dense, searing heart. For untold years, it fought its way through the sun's interior, scattering and dancing through the radiative maze, slowly migrating to the surface. At last, it broke free from the photosphere, joining the radiant tide of sunlight that floods out into the darkness. In that instant, it set out across the cosmic gulf at the ultimate speed, racing through the vacuum toward our small planet. After a brief voyage through the abyss of space, the photon pierces Earth's upper atmosphere. Perhaps it is dawn, and this tiny messenger of the day slips through a clear sky to reach a waiting leaf on a tree. The photon is absorbed, its energy triggering the chemistry of life, photosynthesis, helping a green leaf turn carbon dioxide and water into sugar. In that moment, a bit of the sun's energy, carried across the cold void by a single photon, becomes part of a living plant. Another photon falls upon a human face and is absorbed in the warm skin of someone standing under the morning sun. Nerves register the gentle heat. The mind welcomes the comfort. That warmth is a direct touch from our star, a tangible link between our flesh and the nuclear fires at the sun's heart. Every ray of daylight that we see, every soft beam reflected by the moon at night, began in the sun's core long ago. The sunshine that makes the petals of a flower glow, that draws a child's laughter on a bright afternoon, that dances on waves at dusk. All of it is energy forged in a star and sent outward as a gift across the emptiness. It is literally starlight. The light sustains the winds and rains of Earth's weather, drives the engines of life, and paints our world in color each sunrise and sunset. From the sun's perspective, these photons are a way it reaches into the darkness, touching worlds with its essence. From our perspective, they are life and time itself. Every meal we eat is sunlight captured by plants. Every sight we behold is enabled by the sun's illumination. Thus, the sunlight we feel on our skin carries an ancient story. It is the end of a journey that began in the heart of a star and a bridge between our everyday lives and cosmic processes. In that golden glow, the tumult of the sun's interior and the fury of its storms are gentled into a nurturing radiance that gives life rather than takes it. We are, in every sense, bathing in the light of a star. To stand in the sunshine is to be touched by the cosmos, to be warmed by a process that has been ongoing for eons. The next time you see dust motes dancing in a sunbeam or feel the sun's warmth on your face, remember that you are feeling the afterglow of a journey that spanned the depths of space and countless years, a journey from the core of a star to the core of your being. Beyond the orbit of Earth,
the Sun's influence continues in a quieter but no less significant form. The solar wind that billows out from the corona fills the solar system with a tenuous, invisible presence. Space is not truly empty. It is filled with the Sun's breath. This stream of charged particles flows outward past all the planets, carrying with it a stretched-out imprint of the Sun's magnetic field. It's as if the Sun, through its wind, reaches out to touch each world in its orbit, linking them in a web of invisible threads. As the solar wind encounters each planet, the effects depend on whether the planet is protected by its own magnetic field or left exposed. We've seen how Earth's magnetic bubble deflects the wind, diverting the charged particles around us. Jupiter and the other giant planets have formidable magnetic fields that carve out even larger sanctuaries in the solar wind. When the solar wind presses against these magnetic bubbles, it sparks auroras at their poles too. Jupiter's polar skies glow with curtains of light far more intense than Earth's, and even Saturn wears ethereal rings of auroral light. On worlds like Mercury or our Moon, which have little or no magnetic shielding, the solar wind slams directly into the surface. It can embed particles in the soil and slowly sputter away atoms into space. Mars, with only patchy magnetic fields and a thin atmosphere, has its skies occasionally set aglow by diffuse auroras, a reminder that even without a strong magnetosphere, the solar wind still makes its presence known. Perhaps the most visually stunning evidence of the solar wind's reach is found in comets. When a comet from the frigid outer reaches of the solar system ventures close to the Sun, it sprouts a luminous tail that always points away from the Sun. This is because the solar wind, along with the gentle pressure of sunlight, is pushing material off the comet's nucleus and sweeping it into a tail that streams far into space. Every comet's tail is essentially a windsock, revealing the direction of the Sun's breeze. In ancient times, people saw those mysterious comets with their glowing tails stretching across the sky, and perhaps sensed that the Sun and the comet were interacting. Now we know it is the breath of the Sun, gusting through space, that draws those ephemeral streaks. The solar wind is not a steady, featureless breeze. It has structure and gustiness. Fast streams of solar wind can overtake slower ones, creating turbulent regions out in the depths of space. Magnetic clouds and shock waves from solar eruptions course through the wind, eventually overtaking planets or other spacecraft that lie in their path. The wind also carries the Sun's magnetic polarity outward. At times, Earth finds itself connected to the Sun by magnetic field lines stretching across interplanetary space, allowing energetic particles from solar flares to spiral directly toward us. In this way, the solar wind is the medium that transmits the Sun's influence throughout its domain, like a great cosmic ocean in which the planets sail. As our solar system journeys around the center of the Milky Way, it carries this protective bubble along. The Sun, like a bee in a giant swarm, orbits the galactic core among billions of other stars. One lap around the galaxy takes an unimaginably long time. In the Sun's long life so far, it has only managed a few dozen such circuits. On this grand voyage, our star drifts through changing cosmic neighborhoods. Sometimes the space around it is relatively empty. At other times it might encounter wisps of nebulae or the lingering echoes of ancient supernovae. These encounters can subtly influence the boundary of our heliosphere, perhaps even nudge comets from the distant cloud at the fringes of our solar system. We ride along on this stellar odyssey, a family of planets wrapped in the Sun's embrace, cruising through the galaxy's spiral arms. It is a humbling thought that our entire existence, every life, every story told under the sun, has been carried on this great galactic journey, and it will continue long after we are gone, the Sun forging ahead through the dark with its tiny companions in tow. Eventually, at some immense distance from the Sun, the solar wind begins to meet resistance. The sparse gas that drifts between the stars pushes back against the sun's advancing wind. The solar wind slows, compresses, and finally, at a certain boundary, it can push no further. The continuous expansion of the sun's atmosphere is halted by the presence of the wider galaxy. This boundary marks the outer edge of the sun's influence, the frontier of our star's dominion. Here, the solar wind's long journey ends, merging into the interstellar medium. This invisible border defines a vast bubble around the sun, known as the heliosphere, a cocoon of solar particles and magnetic fields that envelops all the planets. To step outside that bubble is to enter truly interstellar space. For decades, the solar wind was only a theory, an idea to explain why comet tails always point away from the sun. It wasn't until humanity ventured into space with probes that we felt this wind firsthand. Our spacecraft have measured its particles and tasted its composition. Finally, after decades of journeying, a tiny spacecraft built by human hands passed through the boundary of the heliosphere and sailed into interstellar space, becoming the first emissary from Earth to enter the realm between the stars. It confirmed the existence of that distant frontier and carried with it a golden greeting from our world as it moved under the dim light of a sun now far behind. The sun's breath, it turns out, has a limit. Within that limit, within that bubble, the sun is Lord and life-giver. Every world we have ever known lies inside this protective sheath blown by our star. Now, standing at the edge of the heliosphere, we gaze outward and backward to the realm of the galaxy beyond, and backward toward the sun at the center of its bubble. We can appreciate the true scale of our star's influence. The sun is not just a disk in our sky. It commands a vast region of space, sculpting it with light and wind. It has forged a safe haven in the Galactic Sea, a place where its family of planets resides. To understand the sun fully, we must also understand how stars like it are born and how they die. For our sun is one among billions, each with its own story of origin and fate. Our journey now moves beyond our solar system, beyond the present moment of our sun's life, to the story of how such stars come into being and how they transform over time. Stars are born in darkness, far from the bright bustle of any galactic core, in the quiet spiral arms of galaxies like our Milky Way. Vast clouds of gas and dust drift in cold obscurity. These are the stellar nurseries, enormous nebulae stretching across light years of space, rich in hydrogen and sprinkled with heavier elements forged in ancient supernovae. Within these great clouds, gravity works patiently and silently. A slight densification, perhaps triggered by the shockwave of a distant exploding star or the brushing encounter of two clouds, begins to draw matter toward its center. As the gas compresses, it heats up and starts to glow faintly. What was once invisible in the darkness becomes a warm ember hidden inside a cocoon of dust. This is the birth of a star, or rather, the first whisper of a star yet to be. As the cloud fragment collapses under its own weight, it often breaks into smaller pieces, each destined to form a star, or even a small cluster of stars. In each fragment, matter spirals inward, and as it falls, it begins to spin faster, like a twirling ice skater pulling in her arms. A flattened disk of gas and dust forms around the growing central mass, whirling like a carousel. At the center of each collapsing fragment, a protostar, a baby star, is taking shape. It is not yet a true star, for it has not begun nuclear fusion, but it shines with the heat of its gravitational contraction. We can imagine it as a glowing orb buried deep within a dusty womb. If we could pull back the veil of dust and look inside, we would see a scene both serene and violent. The protostar's surface roiling with convection, jets of gas erupting from its poles and piercing out into space, and the surrounding disk feeding material steadily onto the growing stellar infant. In these concealed cradles, many stars are often born together,
siblings in a stellar brood. Some are destined to be massive and brilliant, others small and faint. For a brief time, the protostar continues to gather mass. The infalling gas rains down mostly onto the disk, which then funnels onto the star. The star grows, and the pressure and temperature at its center climb ever higher. When the core temperature at last soars to the threshold, where hydrogen atoms begin to fuse into helium, a profound transformation occurs. The protostar becomes a star. It is as if a switch is flipped in its core. The darkness inside ignites into light. The star begins to generate its own energy by the same nuclear process that powers our sun, and a new sun bursts into existence in that once dark place. With that first ignition of fusion, a stellar wind, much like the solar wind of our sun, often springs from the newborn star, and intense light from the hot young star pours into the surrounding space. These forces blow away the remaining shreds of the natal cloud, dispersing the cocoon that once hid the star. If the star is massive enough, its fierce radiation may carve fantastic shapes in the parent nebula, creating glowing cavities and pillars of dust that resist the onslaught for a time. Before long, what was once an opaque dark cloud becomes a cluster of shining new stars, its birth cloud eroded to wisps around them. The siblings now bask in each other's light as they drift together, loosely bound by gravity. Our own sun was likely born in such a cluster of stars. It may have had many siblings forming alongside it in a long-vanished nebula, all of them cocooned together and then emerging into the galaxy's light. In that stellar nursery, the sun's siblings would have shone nearby, sharing a common region of space for a time. But over the ages, the cluster dispersed. Each star, including our sun, went its own way, moving through different orbits around the Milky Way. Today, the sun's sisters and brothers are scattered, indistinguishable from the other stars of the galaxy, though astronomers scanning the sky have identified a few stars with chemical fingerprints so similar to the sun's that they might be long-lost solar siblings. In the collapse of a nebula and the birth of a star, we see nature's cycle of creation at work. The gas and dust that form new stars carry the ashes of previous generations, the carbon that will someday course through the veins of living creatures, the oxygen that will fill their lungs, the silicon that will form rocky worlds. All these atoms were fused in stars that lived and died before our sun was born, then mixed into the clouds from which new stars arise. Each generation of stars enriches the galaxy further, seeding the raw material for planets and life. Thus, when a new star like our sun ignites, it carries within it the legacy of cosmic ancestry. Around many newborn stars, the leftover gas and dust in the disk coalesce into smaller clumps, giving birth to planets, moons, comets, and asteroids, the makings of a new solar system accompanying the new sun. From afar, a stellar nursery like the Orion Nebula offers us a glimpse of this wondrous process. Through telescopes, we see stellar embryos still swaddled in dust, others breaking free and burning blue-white with youthful energy. We see great columns of dark gas, cosmic pillars, being eroded by the radiation of hot young stars hidden within them. In that radiant chaos, worlds are being formed, and light that will shine for billions of years is first kindled. Star birth is at once delicate and cataclysmic. Delicate in the slow, inexorable gathering of a star's first light, and cataclysmic in the way a newborn star's brilliance can rip apart the very cloud that gave it life. From these nurseries emerge all stars, whether destined to be mighty blue giants or dim red dwarfs. The process is the same, guided by the pull of gravity and the laws of physics that govern heat, pressure, and fusion. We have journeyed from our sun's neighborhood out into the broader galaxy to witness the origin of stars. Now, having seen how stars take their first breath, we can explore the grand tapestry of stellar variety. the many kinds of stars that fill the cosmos, from the smallest embers to the most luminous beacons. The stars that populate the universe are as diverse as the creatures in a great ocean. They come in different sizes, colors, and brightnesses, each type with its own character. Astronomers classify stars by their temperature and luminosity, which often correlates with color. Just as iron glowing in a blacksmith's forge changes from dull red to orange to white hot as it gets hotter, a star's color tells us its heat. The coolest stars are deep red, smoldering with a subdued cherry glow. Hotter stars shine in yellow and white hues. The very hottest stars blaze with blue-white brilliance, their surfaces incredibly hot. The smallest true stars in the cosmos are the red dwarfs. These diminutive stars contain only a small fraction of the sun's mass and glow feebly, often with a light so faint that none are visible to the naked eye from Earth, despite being the most numerous stars in the galaxy. A red dwarf is usually much smaller and cooler than our sun, giving off a ruddy light. But what they lack in brightness, they make up in longevity and ubiquity. The vast majority of stars in the Milky Way are thought to be red dwarfs, quietly burning their fuel at a glacial pace. A red dwarf may live for an almost eternal span of time before it runs out of fuel. In these diminutive furnaces, the flame of nuclear fusion is weak but extraordinarily steady. Some of the smallest red dwarfs can continue to shine for longer than the current age of the universe. On the other end of the stellar spectrum are the blue giants and supergiants. These stars are born with many times the mass of the sun. They are extremely hot and brilliant, shining with a fierce blue-white light that can be seen across great distances. A blue giant star pours out an enormous amount of energy, consuming its hydrogen fuel at a prodigious rate. Because of this, its life is intense and fleeting. It will exhaust its core fuel in a cosmic eye blink, a mere moment compared to the tranquil longevity of a star like our sun. Some of these massive stars do not stay blue-white for their whole lives. As they age, they swell and cool, turning into red supergiants that can be truly colossal in size, their bloated atmospheres expanding outward to stupendous dimensions. Imagine a star so large that, were it placed where our sun is, it would extend beyond the orbit of Earth and well into the realm of Mars. These red supergiants glow with a cooler, reddish light, but they are tremendously luminous due to their sheer size. They are rare and splendid beacons in galaxies, heralds of impending cosmic change, for they live fast and die spectacularly. Between these extremes lies a rich variety of stars. There are orange dwarfs, slightly smaller and cooler than the sun. There are white stars, somewhat hotter and more massive than the sun. And there are stars like our own, yellow-white and medium-sized, often called main sequence stars or dwarf stars by astronomers. Our sun, in fact, is considered a dwarf star in this sense, not because it is especially small. It is larger and more massive than most stars, but because it is in the prime of its life, steadily fusing hydrogen in its core. It hasn't yet bloomed into a giant. In terms of mass and brightness, the sun is fairly average, but because the faint red dwarfs are so inconspicuous to our eyes, most of the individual stars that dazzle us in the night sky are actually more luminous than our sun. Many of the bright stars we see at night are larger, hotter, or more energetic than the sun, which is why they stand out from afar. Meanwhile, countless dim red stars nearer to us go unnoticed without a telescope. Stellar classification also includes exotic categories. There are the supergiants we mentioned, both blue and red, which are essentially stars on steroids, far larger and more luminous than ordinary stars. And there are stars at the very brink of not being stars at all. The brown dwarfs, sometimes nicknamed failed stars. These objects form in the manner of stars but do not accumulate enough mass to ignite sustained hydrogen fusion in their cores.
A brown dwarf glows faintly with leftover heat from its formation, and perhaps with brief flashes of fusion of heavier forms of hydrogen, but it gradually cools and fades, acting more like a giant planet than a true star. Brown dwarfs fill the gap between the largest planets and the smallest red dwarfs, and they add to the menagerie of objects in the galaxy. Nature produces stars in a continuum of masses and sizes, from tiny red embers that burn for practically eternity to stellar titans that blaze with incredible intensity and then perish in the blink of an eye. Each type of star has its own destiny. A star's mass, set at birth, is the key that unlocks the rest of its life story. With a high mass comes a glorious but short-lived existence as a giant, likely ending in a dramatic explosion. With a low mass comes a long, steady burn and a quiet retirement. Having surveyed the variety of stars, the small, the medium, the great, we can now follow one typical star, perhaps not unlike our sun, through the stages of its life, from its youthful radiance to its final farewell. Let us trace the fate of a star much like our sun, now that it has burned in the heavens for eons. For a long time, such a star shines steadily, fusing hydrogen into helium in its core and bathing any nearby worlds in stable light. But the fuel at its center is finite. Eventually, after many billions of years of shining, the hydrogen in the core dwindles. The balance that sustained the star for so long begins to tip. With less fusion to support it, the core of the star starts to contract under its own gravity. As it contracts, it heats up, much as a bicycle pump grows warm when you compress the air inside. This extra heat flows into the shell of hydrogen that surrounds the inert core, a shell that still has hydrogen left to burn. And then something dramatic happens. Hydrogen in this outer shell, now at extreme temperatures thanks to the contracting core beneath, ignites in fusion. The sudden onset of shell burning causes the star's outer layers to push outward. The star swells enormously in size, turning into what we call a red giant. Its surface cools as it expands, shifting from yellow-white to orange-red. But the star's interior becomes hotter than ever, and its luminosity soars due to its sheer size. Our once modest sun-like star becomes a bloated colossus. In this red giant phase, the star's radius can grow far larger than it was in its youth. If our sun were to undergo this transformation, it would likely engulf Mercury and Venus, and perhaps even Earth, turning those worlds into charred cinders swallowed by the expanding stellar fire. The sky of any surviving outer planets would be dominated by the star's enormous disk, a brilliant coppery orb covering a huge swath of the heavens. Deep inside the red giant, the core continues to shrink and heat, as it is now made mostly of helium ash, the byproduct of those long ages of hydrogen fusion. When the core grows hot enough, a new kind of fusion begins. Helium atoms start fusing together to form carbon and some oxygen. Our star, which was facing death, finds a second wind. The onset of helium fusion in the core, often beginning in a sudden burst for a sun-like star, something astronomers poetically call the helium flash, stabilizes the star for a time. The core expands a little and cools, and the star's bloated outer layers contract somewhat from their extreme size. The star settles into a new equilibrium, a helium-burning giant. In this phase, the star's color might become a bit more yellowish as it slightly shrinks, and its surface temperature rises again, and it burns steadily once more, though its remaining lifetime is now comparatively brief. But helium, too, is a finite fuel. In time, the core's helium is exhausted, leaving an inert mass of carbon and oxygen, the carbon and oxygen that were created by the helium fusion. For a star like our Sun, no further fusion is possible in the core. The temperatures required to ignite carbon are beyond its reach. With fusion ceasing again in the center, the core of the star, now a dense ball of carbon and oxygen, contracts yet further. Meanwhile, Helium fusion may continue in a shell around the core, with hydrogen fusion still going in a shell above that for a while. This causes the star to swell once more, even larger than before. The giant star becomes highly unstable in this final stretch of its life. It pulsates, growing and shrinking, trying to find balance, but never quite succeeding. Each expansion and contraction shakes loose some of the star's outer layers. Gentle at first, these pulsations turn into violent throes that throw vast clouds of the star's outer atmosphere into space. The star is literally coughing away its own substance, shedding its mass like tears into the void. Eventually, the entire outer envelope of the star is cast off, blown away into space as a gorgeous gossamer shell of gas. For a brief time, that expanding shell is illuminated by the hot, exposed core at the center, and it shines as a glowing, multicolored cloud known as a planetary nebula. To an observer afar, it is a sight of eerie beauty. A round or ring-shaped mist, glowing where once there was a star, often with intricate patterns like delicate rings or hourglass forms. This is the dying breath of a star like the sun, a final gesture of beauty as its outer layers, now free in space, fluoresce in the stellar twilight. What remains of the star itself is the central core, now revealed, a ball of carbon and oxygen about the size of Earth, tremendously hot but no longer sustained by fusion. This is a white dwarf, the ember of a star's heart. It glows white-blue with residual heat, initially extremely hot, though its small size means its total light output is relatively modest. A white dwarf is one of the strangest forms of matter in the universe. It is supported not by heat or ongoing fusion, but by the quantum pressure of electrons, a fundamental resistance of matter to further compression. Its density defies imagination, the mass of a sun compressed into a sphere the size of a planet. A spoonful of white dwarf material would outweigh a mountain. In this exotic, degenerate state, the stellar core will sit and slowly cool for time spans beyond human comprehension, fading from white to yellow to red, and eventually toward blackness. Thus ends the life of a sun-like star, not with a bang, but with a serene, farewell glow. The mighty red giant's cast-off shroud becomes part of the galaxy, seeding space once more with elements like carbon and oxygen that will one day find their way into new nebulae, new stars, new planets, and perhaps new living beings. The white dwarf that remains is like a stellar tombstone, an extremely dense crystal of carbon and oxygen. Some have likened a white dwarf to a cosmic diamond, marking where a shining sun once lived. Over eons, it will cool further and dim, eventually becoming a black dwarf, a hypothetical cold dark sphere, the final quiet cinder of a once radiant star. The universe, however, is not yet old enough for any white dwarfs to have cooled completely to black. That final stage lies in the far future, far beyond the present age of the cosmos. Our sun will one day follow this very path. It is the destiny of all stars in its weight class. But not all stars share the same fate. The most massive stars, those bright blue giants we discussed, live dramatically different lives and meet far more violent ends. Before we return to the personal tale of our own sun's future, let us first briefly touch on the spectacular final act of those heavier suns, a fate that leaves behind some of the most enigmatic objects in the cosmos. While a star like the sun ends its life in relative peace, the same cannot be said for the giants. The most massive stars go out with staggering violence. After burning through hydrogen and helium in a cosmic rush, a high-mass star, far more massive than our sun, doesn't stop at carbon and oxygen. Its core, under tremendous gravity, continues fusing heavier and heavier elements in layers, like the layers of an onion. Carbon fuses into neon, neon into oxygen, oxygen into silicon, each stage burning faster and yielding less energy than the last. Finally,
the core is transmuted into iron, the ash of nuclear fusion, an element that cannot release energy by fusing further. When enough iron accumulates in the core, the star faces an irreversible crisis. With no new energy to support it, the iron core collapses in on itself in a fraction of a second. The core implodes, and densities reach such extremes that atoms are crushed. Protons and electrons melt into neutrons. The core, which was once perhaps the size of Earth or smaller, shrinks to a sphere only a few miles across in an instant. In that moment of collapse, a phenomenal amount of gravitational energy is released. The infalling outer layers of the star hit this super-dense core and rebound outward in a titanic explosion, a supernova. The star's death throes are so violent that for a brief time, the exploding star can outshine all the billions of other stars in its galaxy combined. The supernova blasts the star's outer layers into space at incredible speeds, and shockwaves race through the expanding debris. Temperatures in the explosion briefly soar so high that elements heavier than iron are forged in the fiery crucible. Gold, silver, uranium, and many others are synthesized in those final furious seconds. These newly minted atoms are hurled into the cosmos to mingle with the gas and dust that will eventually form new stars and planets. What remains at the center of this cataclysm is the collapsed core. If the star was only moderately massive, on the lower end of the massive star range, the core's collapse is halted by the pressure of densely packed neutrons. Matter squeezed so tightly that the neutrons resist any further compression. The core becomes a neutron star, an object of incredible density and exotic nature. A neutron star packs more mass than our Sun into a sphere only a few tens of miles wide. It is essentially a giant atomic nucleus, a ball of neutrons left behind by the supernova. A thimbleful of neutron star material would outweigh a mountain. Neutron stars often spin rapidly. The parent star's rotation speeds up dramatically as it collapses, like a pirouetting skater pulling in her arms, and they may possess intense magnetic fields. Some neutron stars sweep beams of radiation from their magnetic poles as they spin, like lighthouses in the cosmos. These are observed as pulsars, blinking radio or X-ray beacons, marking the location of a neutron star across the galaxy. For the most massive of massive stars, even neutron degeneracy pressure cannot hold the core up. If the collapsed core is above a certain critical mass, nothing known can stop its collapse. It continues to shrink until it essentially vanishes from view, forming a black hole. In that case, the stellar remnant has crushed itself into a point of virtually infinite density, enveloped by a region of space from which nothing can escape. Not even light can climb out of the warped space around the collapsed core, hence the name black hole. What was once the heart of a star becomes a kind of cosmic abyss, a pit in the fabric of the universe. A black hole can be thought of as the star's ultimate tombstone, carrying its mass hidden within a distortion of space-time. We infer its presence only by ghostly tracers, the desperate whirl of gas and dust spiraling into invisibility, flaring in X-rays as it vanishes, or the subtle quivering of space-time itself when the black hole is jarred by the fall of something massive. When a supernova finally fades, it leaves behind these strange remnants, a neutron star or a black hole, and an expanding cloud of gas and dust that was once the star's outer layers. In time, that cloud will cool and disperse into the interstellar medium. The elements cast into space will blend with other matter and eventually become part of new stars, new planets, and perhaps new life. Massive stars, though few in number compared to red dwarfs, are the great alchemists and fireworks of the universe. In dying, they sow the heavy elements across the galaxy, the very elements that make rocky planets and organic beings possible. Every atom of calcium in your bones, of iron in your blood, was forged in the belly of a star that ended in such a blaze. The cosmic ashes of supernovae fertilize the galaxies, ensuring that each new generation of stars is born with a richer array of ingredients for planets and for life. We have traced the lives of stars from gentle birth in nebulae to either a quiet sunset as a white dwarf or a cataclysmic finale as a neutron star or black hole. But our exploration of suns would be incomplete without considering that stars rarely live in isolation. Most have companions or families of their own, multiple star systems bound in gravitational dances, or retinues of planets that circle around them. Our sun itself has a family, the planets, including Earth, and smaller bodies that formed from the disk of dust left over from the sun's birth. And many stars form in pairs or trios, locked in orbits around each other. To truly understand the nature of suns, we must also look at these relationships, the celestial communities that stars form, and the diverse planetary systems that have arisen around distant suns. Each star in the night sky is a sun in its own right, and many are far from solitary. In fact, most stars are born as multiples, two or more suns bound together by gravity, orbiting a common center. Imagine a binary star system, two suns locked in an elegant dance, circling each other over years or centuries. From a distance, they might appear as a single point of light, but up close, each partner star swings through space in response to the other's pull. Some binaries are widely separated, each star carrying its own retinue of planets. Others whirl so close that they can trade gas, or even, in extreme cases, merge into one. In a triple or quadruple system, the dance grows even more complex, with stars tracing intricate paths around their mutual center of mass. The universe is a grand stage with every stellar configuration you can imagine. There are suns that eclipse one another from our viewpoint, causing their combined light to rhythmically dim and brighten, cosmic beacons signaling their orbital waltz. There are stars so close that they share a common envelope of gas, two stellar hearts wrapped in one glowing shroud. And there are systems where small companion stars orbit giant ones in distant loops, like tiny sparks flitting around a great flame. Around many of these suns, planets coalesce and circle, for planet-making is a natural companion to star-making. When a star is born from a spinning disk of dust and gas, the leftover material often forms worlds. Our own solar system is one example, a handful of major planets and a retinue of smaller bodies. And we have learned that planets are astonishingly common. We now know that planets accompany stars throughout the galaxy. Astronomers have discovered innumerable exoplanets orbiting distant suns, and they suspect that for every star we see, there are likely worlds in attendance. There are planets that cling close to their stars, scorched and locked by gravity, so that one hemisphere endures endless day while the other is in perpetual night. There are planets at just the right distances from their suns, the so-called habitable zones, where conditions might allow liquid water and the chemistry of life. Some planets orbit twin suns, experiencing double sunrises and double sunsets, their skies graced by two stellar disks. Imagine standing on such a world, with two faint shadows dancing on the ground, or on a world under a dim red dwarf sun, where the daylight is a brooding ember, and the stars' frequent flares paint the sky with sudden ruddy hues. Each planetary system is a story of creation, just as every star's life is a story. Some stars have giant guardian planets that shield inner worlds from comet bombardments, as Jupiter helps shield Earth. Others have planets in wild, elongated orbits, leading to chaotic swings of climate. Some massive stars might not host long-lived planets at all, as their fierce radiation and short lives can blast away or outlast any nascent worlds. But around the more common, steady stars, the red dwarfs, the orange dwarfs, the sun-like stars, there are surely many planets that have persisted for eons, perhaps even giving rise to life. Under alien suns, if life has blossomed, creatures might gaze up and see a sky tinted by a different color of star and wonder about the warmth that gives them life. just as we ponder our sun. For us, those other suns have been points of curiosity and imagination for as long as we've had eyes to see the stars. Only recently have we begun to detect some of their planets directly, to see the telltale dip in a star's light as an orbiting world passes in front of it, or to measure the slight wobble of a star tugged by the gravity of unseen companions. Each discovery is a revelation, proof that our sun and its family are not unique, that the cosmos is filled with solar systems. It humbles us, yet also makes the universe feel more intimate. A place where countless stars shine down on their own worlds, as the sun does on ours. Now, after journeying so far through stellar nurseries, fiery demises, and distant solar systems, we return our focus to our own star, the sun, and reflect on its ultimate destiny, and on what it means for us to live beside a star. And so we return to our sun, the star that has accompanied every moment of humanity's existence and that sustains all life on Earth. The sun today is a middle-aged star, steadily burning its fuel and kindly bathing our world in light. It has shone in our skies for longer than any living thing can remember, and will continue to shine for ages to come. But the sun, too, is mortal in the cosmic sense. Nothing in the universe lasts forever, not even a star. In the far future, long after our species and all we know may have turned to dust, the sun will begin to change. When its core can no longer sustain the fusion of hydrogen, it will respond by growing in size and luminosity. Our sun, so familiar and constant, will swell into a red giant. Its light will turn the color of copper and blood, and it will loom colossal in the sky. The innermost planets will be engulfed in its fire. Mercury and Venus will surely be devoured. Earth may meet the same fate, or be left a charred and barren rock, its oceans boiled away, its surface desolate and scorched. For any life remaining then, these changes will be catastrophic beyond measure. But likely, by that distant era, Earth will already be quiet and lifeless, or life, if intelligent and capable, will have found refuge elsewhere. The sun, once a gentle guardian, will become an inexorable destroyer of the very life it once nurtured. Yet even in this fierce transformation, there is a strange grandeur. As the sun's red giant phase reaches its climax, it will cast off its outer layers. Our star will shed its shining mantle, which will expand outward, drifting into space. For a short time, those cast-off layers will form a beautiful planetary nebula around the dying sun, a glowing testament to its passing glory. Future astronomers, perhaps from other surviving worlds or civilizations yet unimagined, might look toward our solar system and see a delicate shell of gas, like a cosmic flower blossoming and fading, shining in remembrance of the star that was. At the center of that nebula will remain the sun's core, now exposed and shrunken to a white dwarf. This final stage of our sun's life will be a small, hot sphere no larger than Earth, composed mostly of carbon and oxygen. The sun's very heart, left glowing like a lonely ember in the night. It will shine white and then blue-white, slowly cooling over the course of billions of years. The brilliance of the day that once was will recede into a gentle twilight. The white dwarf sun will illuminate the ghostly nebula for some thousands of years, but eventually it too will fade, perhaps becoming a black dwarf in the far, far future. The solar system will drift in darkness and silence. This is the ultimate fate of our sun, to swell in glory and then to divest itself of its brilliance, leaving behind a small, dense core that will quietly glow and then dim to darkness. It is a fate that the sun will meet far in the future, an inconceivable gulf of time beyond our lives. In knowing this, we find both melancholy and solace. Melancholy that all things we know are transient, that even the great sun will one day wither and leave the sky empty. Solace that we and our world have yet long epochs in which to live under the sun's light, and that when the end comes,
It will be part of the natural order of the cosmos. The same finale that countless sun-like stars have already played out in the quiet reaches of the galaxy. And perhaps, too, there is a kind of triumph in this ending. The sun's final nebula will return its substance to space, enriching the interstellar clouds with elements that once made up Earth and us, and every living thing that sunlight ever touched. In that way, the sun's death will seed new beginnings elsewhere. Some of the carbon and oxygen from the sun's core might drift for ages and eventually become part of new stars, new planets, new life. As it has always been in the universe, one star's end is another's beginning in the endless cycle of creation. Now, stepping back from this entire journey, from the birth of stars in dark nebulae to the blaze of supernovae, from the quiet glow of the sun's youth to its fiery demise, we find ourselves contemplating what it means to be the children of a star. To live beside a star is to live in a state of grace between wonder and knowledge. We orbit a massive, luminous being that gives us everything: light, warmth, the very possibility of life, and yet asks nothing in return. Our ancestors felt the sun's power and worshipped it. They built legends and monuments to honor it. We, with all our modern understanding, have not lost that reverence. How could we? Each dawn when sunlight spills over the horizon, painting the sky in rose and gold, we feel the same awe that ancient watchers felt as the morning star ascended. In that daily miracle, night yields to day, cold yields to warmth, and the world is renewed. We know the science of it. The earth is turning, bringing us once more into the sun's light. But knowing takes nothing away from the magic of feeling it. Beneath the facts and figures, there is a simple truth. The sun is the source of our being. Every meal we eat is sustained by sunlight captured by plants. Every warm breeze that caresses our skin, every drop of rain that falls, is driven by the sun's heat, nurturing our planet. And our bodies themselves are made of material created in long-dead stars and powered by the sun's current light. We truly are made of stardust, shaped into conscious form and given the spark of life by a star's energy. In a very literal sense, we are children of the stars. When we say we are born of starlight, it is not just poetry, it is lineage. The elements in our flesh were brewed in stellar furnaces, and the energy that ignites our living cells is a gift from our sun. Our story and the sun's story are inseparable. Think of the connection. A baby born on a bright morning, crying out with lungs filled for the first time. Those lungs draw in oxygen that a star, billions of years ago, forged in its core and then cast into space. The baby's parents smile in the sunlight that streams through the window, sunlight that left the sun just moments earlier, having traveled across empty space to fall upon that new face. A chain of events spanning eons and light years has culminated in that ordinary, extraordinary moment. Starlight becomes life. The cycle continues. Standing here on Earth, we look up and see a blue sky by day. But beyond that blue lies the black tapestry of space and the brilliant stars. Our sun is one among many, and though we cannot see those others by day, they are there, distant and shining. At night, when our sun has set, we glimpse the wider cosmos of which our star is a part. We see the Milky Way's misty band, made of uncountable suns, and we realize that our little home orbits just one humble star on the edge of a vast galaxy. The humility of this perspective is profound, yet it does not diminish us. It elevates us. We are part of something immense and beautiful. The stars that speckle the night sky are our cousins. Some may have planets with beings who look up at their own sun and feel the same wonder. In the end, the story of suns is the story of creation itself. It is an ancient tale, told in the language of light and gravity. It began before we were here and will continue long after we are gone. But for a brief moment, we get to be conscious participants in this grand drama. We get to study the sun, protect ourselves from its tantrums, bask in its warmth, and dream under its light. Our lives, like mayflies, flicker in the daylight of this star. But while we are here, we behold the splendor of the cosmos through the window that our sun's light provides.
As we conclude this journey, imagine once more the sun hanging low at dusk. The sky blazes with color, and the shadows grow long. In that sunset is a reflection of the entire epic. Day turning to night as stars appear one by one, the cycle of light and dark that has guided life's rhythm from the beginning. The sun will rise again tomorrow, as it always does, bringing a new day. But even when it eventually rises no more, the legacy of its light will live on in everything it touched. We live on the brink of a star's fiery grace, taking our nourishment from its hand and daring to learn its secrets. We are small, but we are also a way for the universe to know itself. Matter that was once scattered across space, now gathered and alive, pondering the star that gave it life. In the dance of sunlight and shadow, we find meaning, comfort, and inspiration. Our sun connects us to the universe and to each other, a common star, binding all living things in a shared radiance. So when you next stand in daylight, feel that warmth and remember, you are heir to an ancient covenant between earth and sun. Every photon that touches you carries a message from that central fire, that life is precious and intertwined with the cosmos. Our world exists because a star shines. And in the atomic hearts of stars, in the silent roaring of their nuclear fires, in the gentle glow that crosses the void, the universe has found a way to nurture consciousness and wonder. This knowledge, this feeling, is humbling and uplifting all at once.
The saga of suns is indeed a cosmic poem, forged in light, breath, and gravity. It is written across the heavens in the glow of nebulae and the ashes of supernovae, in the rising of each morning sun and the eternal glitter of the night. It is a poem we are part of, every one of us made of star stuff and sustained by starlight. In knowing this, we find not despair at our smallness, but gratitude and awe that we have the privilege to dance in the light of a star, and through that light, to glimpse the eternal.